The universe isn't just big, it's weaponized by distance, turning light into a speed limit and dreams into deadlines. One honest scale model, one set of real numbers, and our entire cosmic future starts to collapse. So when you measure it without fantasy, are we a civilization trapped on a speck with the stars effectively out of reach? You've been told the universe is big, but you were never told what big does to hope. Measured honestly, size becomes a weapon against time, against travel, against every civilization's plans. Look up at the night sky and your mind offers comfort. Dots, distances, a ceiling you can imagine. But the universe is not a picture. It is a schedule, an energy bill, and a chain of delays. In space, distance is not scenery. It is what happens to messages, to bodies, to ambitions. We live on a world that feels central because our senses were built for forests and shorelines. So we shrink the cosmos into metaphors. Near, far, the edge, beyond, and we move on. This documentary refuses the metaphor and replaces it with numbers that do not negotiate. We will measure the solar system in light time because light exposes what maps politely hide. We will follow the farthest thing we have ever built and ask why its triumph still feels local. Then we widen the frame until the Milky Way stops being a band of starlight and becomes a structure. A structure with a crossing time so vast that history itself becomes the unit of travel. And we will keep climbing rung by rung into the local group, our island of gravity and black water. Beyond that island, space does something stranger than emptiness. It expands and it accelerates. Not as an explosion from a center, but as a stretching of the ruler you thought you trusted. At a certain scale, destinations recede faster than any ship can catch, without breaking any law. That is where the central question hardens into something colder than curiosity. When we count honestly, are we small enough to be trapped? Not trapped by a lack of imagination, but by the physics of energy, the fragility of biology, and the tyranny of time. Because every increase in speed demands a steeper price, and every shield becomes more mass to push. Because even a perfect plan must survive boredom, error, radiation, and centuries that turn into millennia. And because the universe does not merely dwarf us, it separates us with horizons, the way an ocean separates islands. Some horizons are close, fading at the boundary where the sun's influence thins into interstellar dark. Some are galactic, written across a disk of stars whose light reaches us already ancient. And some are cosmic, where expansion turns other galaxies into distant ghosts, visible but not reachable. If that sounds like despair, wait, because limits can also be instructions. If bodies cannot go, perhaps instruments can. If empires cannot spread, perhaps knowledge can endure. And if the reachable universe is smaller than our dreams, then our duty becomes sharper. Protect the island we can touch, and listen harder into the dark. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. We begin by dismantling the scale traps in your intuition. Then we rebuild reality with light, time, and distance. By the end, you will see why the universe's true terror is not its size, but what that size does next. 10, 9, 8. We start with distances your body can almost picture, the kind you can trace on a globe with your finger. Earth's diameter is about 12,700 kilometers, a number that still feels like geography and weather. You can imagine a jet stream curling over that curve, or a storm system wider than a continent. 7, 6. The moon sits roughly 384,000 kilometers away, close enough to seem reachable in a single thought. In the night sky it looks like a coin, but the coin is a cliff, an ocean of vacuum between. 5, 4. Light crosses that gap in about 1.3 seconds, and the number snaps into focus with a hard edge. If you watched Earth from the moon, you would see it slightly delayed, as if reality had a tiny echo. 3, 2. The sun is 150 million kilometers away, and the mind starts losing traction. The distance is so large that the orbit becomes the story, not the number. 1. Light needs about 8 minutes and 20 seconds to arrive, and time becomes the ruler instead of space. If the sun vanished, the sky would keep shining for those 8 minutes, because information cannot outrun light. 0. The countdown ends, but the scaling does not, and intuition quietly fails in the silence after the last number. Your brain evolved for hunting ranges and storm horizons, not for vacuum and orbital math. Depth perception works because nearby objects shift against a background, yet space offers almost no background at all. We are good at near and far, and terrible at orders of magnitude that multiply instead of add. 1,000 feels like a lot, but 1,000,000 feels like just more, and that is the trap. We compress the unfamiliar until it fits a story, then we mistake the story for reality. That is the scale trap, and it distorts everything we think we know about exploration and what counts as close. It also distorts significance, because size becomes a proxy for importance in human minds, even when physics disagrees. This documentary refuses the story and keeps the arithmetic, because the universe does not negotiate with metaphor. We will measure space the way space forces you to measure it, with tools that admit delay and cost. First, by scale in kilometers and meters when those still help, because engineering begins with concrete numbers. Second, by light time, because light sets the speed limit for information and causality, and nothing cheats that limit. Third, by travel time, because dreams require vehicles, fuel, shielding, and years that must actually pass for crews and hardware. When numbers stop meaning anything, we will convert them back into time and consequence, the only currencies the cosmos reliably accepts. The first tool is the astronomical unit, the average Earth to Sun distance, born from the need to compare orbits. 1 AU is not poetic, it is practical, a baseline for solar system navigation and for the geometry of trajectories. Historically, astronomers fought to measure it, using transits of Venus and careful timing to pin down the scale. Once the AU was known, the solar system stopped being a sketch and became a calibrated machine. Planets, asteroids, and spacecraft trajectories become readable when distances are counted in AU, because the numbers stay human-sized. At this scale, the solar system is not a map. It is a clockwork of moving targets, each one sliding along an ellipse. Next come light seconds and light minutes, the units that expose delay and make distance feel like a pause. A light second is about 300,000 kilometers, and it is a harsh simplifier because it ignores everything but speed. Earth to Moon is a bit over 1 light second, so conversations would always lag, even with perfect equipment. Earth to Sun is about 8 light minutes, so even sunlight is already history by the time it warms your skin. That delay is not philosophical, it is operational, because remote control is never truly real-time at planetary scales. Spacecraft near Mars can be minutes behind, and a mistake cannot be corrected with a quick reflex. These units exist because signals matter, and because command at distance becomes planning rather than steering. Then we jump to the light year, and the jump is the point because the mind needs a cliff to notice the drop. A light year is the distance light travels in 1 year, about 9.5 trillion kilometers, and the number is deliberately unwieldy. It is used because stars are not just far, they are far in a way kilometers cannot hold without becoming noise. When you say a star is 4 light years away, you also say its image is 4 years old, a built-in timestamp. The sky becomes a museum of delayed photons, and every bright point is a message from a different moment. Distance becomes delay, and delay becomes a limit on action, because you cannot respond to what you have not yet learned. Finally, the parsec, built from geometry rather than drama, and favoured because it grows naturally from measurement. A parsec is about 3.26 light years, defined by parallax from Earth's orbit around the Sun. As Earth moves, nearby stars shift slightly against distant ones, and that tiny angle is the clue. Astronomers use parsecs because angles are measurable when absolute distances are not, especially with precise instruments. Parsecs scale cleanly into kiloparsecs and megaparsecs for galaxies and the cosmic web, keeping equations tidy. This is the language of mapping, where the universe becomes coordinates instead of myths, and where uncertainty is tracked honestly. Now we build a ladder, rung by rung, and we do not skip steps. We begin where our instincts still pretend to work, inside the solar system, where sunlight still feels like a local lamp. Mercury is about 0.4 AU from the Sun, and Neptune is about 30 AU out, a spread that already strains imagination. Between them are worlds with radically different temperatures, gravities, and day lengths, yet all share one star's pull. Even here, travel time already punishes impatience, because rockets do not cruise like light and cannot accelerate forever. A fast probe can take years to reach the outer planets, and that is still our backyard by cosmic standards. The visuals are deceptive because textbook diagrams squeeze orbits together until they look like a tidy family portrait. The next rung is the heliosphere, the sun's inflated bubble of solar wind, blown outward like a breath that never stops. This wind is a plasma stream, charged particles threaded with magnetic fields, and it carves a cavity in interstellar space. It is not a clean border, and it is not a wall, but it is a domain with structure and turbulence. Voyager 1 is often described as leaving the solar system, and the phrase hides complexity behind a headline. It crossed the termination shock where the solar wind slows abruptly, and later the heliopause, where solar pressure yields. Instruments sensed changes in particle density and magnetic behavior, the subtle signatures of crossing into a new regime. Yet the sun's gravity and long tail of influence persist, and the definition of leaving keeps moving with the science. Voyager 1 is a lesson in scale, because even our farthest messenger is still close by cosmic standards, still in the sun's extended neighbourhood. Here the distance debt begins to show its teeth, because each rung outward multiplies the bill you must pay in time. Every rung outward multiplies distance, and travel time compounds beyond a human lifetime, even before you add failures and delays. At tens of AU, you can still imagine a mission that launches, arrives, and returns data within one career. At hundreds of AU, you start imagining power sources that fade, antennas that must stay aligned, and computers that must endure. At thousands of AU, you start imagining generations, maintenance, and institutions that must outlive their founders without losing purpose. At light years, you must imagine a civilization staying coherent long enough to finish the trip, and that is a different kind of engineering. The local interstellar neighbourhood is the next rung, and it is mostly emptiness with a few scattered embers. The nearest star system, Alpha Centauri, is about 4.3 light-years away, and that near is a trap word. The space between is not truly empty, but it is thin. Gas, dust, and cosmic rays spread like a faint fog. At the speed of Voyager 1, that journey would take tens of thousands of years, longer than recorded history so far. Even at 1% of light speed, it takes over 4 centuries, longer than many empires last and longer than most languages survive unchanged. Distance debt is not just time, it is risk multiplied by duration, because every component must keep working while the universe keeps happening. We tell ourselves we will go faster, and physics asks with what energy and with what tolerance for heat and radiation. Kinetic energy rises with the square of velocity, so speed is expensive in a deep way that surprises non-engineers. Doubling speed does not double the energy, it quadruples it, and that curve turns ambition into accounting. Fuel is mass, mass is cost, and cost is politics, and politics has a short attention span compared to interstellar timelines. Even if you carry no fuel and use external pushes, you still face shielding, erosion, and the brutal arithmetic of impacts. At high fractions of light speed, even dust grains become bullets, and the interstellar medium becomes a hazard field. A civilization can dream of starships, but it must also pay for them without collapsing first, and that constraint is as real as gravity. The ladder continues into the Milky Way, and the numbers stop behaving like anything you can hold in your head. Our galaxy is about 100,000 light-years across, with a disk and a halo, and both are thicker than they look. The disk is laced with spiral arms, star-forming regions, and dark lanes of dust that hide what they contain. The Sun sits roughly 26,000 light-years from the centre, orbiting once every 200 million years in a slow, steady sweep. That orbit time is a reminder that even galactic motion is slow beyond human narrative, more like geology than travel. When we ask how big the Milky Way really is, we're asking where its edge fades into dark matter and sparse stars. The answer is not a line, it is a gradient, and gradients are hard for brains built for fences and borders. To visualize it, imagine city lights thinning into suburbs, then into scattered farms, until darkness becomes the dominant feature. Inside the Milky Way, distance debt becomes almost absolute for biology, because lifetimes are short and space is wide. A trip to the galactic centre at 10% light speed still takes 260,000 years, even before you slow down. A trip across the disk takes 1 million years, and that assumes engineering we do not yet possess and stability we cannot guarantee. If a species spreads, it does so as a slow wave, not as a heroic sprint, because settlement follows logistics. The romantic image is a ship leaping between stars, but the realistic image is a frontier creeping, pausing, and adapting. Beyond the Milky Way sits Andromeda, our nearest large neighbour, a pale smear that becomes a galaxy in long exposure. It is about 2.5 million light-years away, close in cosmic terms and impossible in human terms. We hear that Andromeda will collide with the Milky Way, and the word collision misleads by implying a crash of solid objects. Galaxies are mostly empty space, so stars rarely hit, but gravity rearranges everything over billions of years. Tidal forces stretch disks, fling stars into long arcs, and feed central black holes with disturbed gas. Whether it is a direct hit or a near miss depends on measurements still being refined, because tiny uncertainties grow across millions of years. Either way, the timescale is so long that it mocks the urgency of any one civilization, and yet it is still part of our local story. Then comes the local group, a small family of galaxies bound by gravity, drifting together in a shared dark matter scaffold. It spans several million light-years and includes dwarfs that orbit like moths around lamps, faint companions easily overlooked. Some dwarfs are being torn apart, leaving stellar streams that wrap around larger galaxies like ghostly ribbons. At this rung, the map becomes sparse, and the void becomes the dominant feature, not as an exception but as the rule. Between groups lie intergalactic distances so large that even light takes tens of millions of years to cross. The universe is not packed with destinations, it is mostly separation, and the separation is what shapes history. Now the final rung for this chapter, the intergalactic void as a concept, and as a warning about what out there really means. Void is not nothing, but it is thin enough to feel like nothing to travellers, a near-perfect darkness between island chains. A few atoms per cubic metre can still matter over millions of years, yet it offers almost no resources and no shelter. It is where the distance debt becomes a wall built from time itself, because the gaps stop being crossable narratives. Even if you could survive the journey, you must keep a mission meaningful across epochs, while cultures and goals inevitably change. What does it mean to launch a plan you will never see completed, and to trust strangers in the far future to care? And then expansion enters, and the ladder tilts away from us, because the background itself is moving. The universe is expanding, and faraway galaxies recede as space stretches between, like dots on a balloon surface. This is not galaxies flying through space like shrapnel, but space itself growing, carrying them along. Beyond a certain distance, recession outpaces any ship that obeys relativity, no matter how long it accelerates. Those galaxies become unreachable islands, visible but forever beyond contact, because the route lengthens faster than you can travel it. This is not pessimism, it is geometry plus a speed limit, and the limit applies to every possible messenger. So the stakes sharpen, because scale is not just a number, it is a verdict written in physics. Our sense of significance is tied to our ability to act, to reach, to change outcomes, and to return with proof. If interstellar travel is effectively impossible for biological civilizations, then our future is local by force, not by choice. If it is possible, it demands patience, energy, and stability on unprecedented levels, sustained across generations without losing direction. Either answer changes what hope means, and what exploration can honestly promise, and what kind of species we must become. This chapter has one job: to rebuild meaning where intuition collapses, and to make the ladder feel like something you climbed. We counted familiar distances until the numbers broke, then we replaced them with light time and travel time, which restore consequence. We named the units that professionals use because they match the structure of reality, not the structure of a story. We climbed the scale ladder from planets to void, and watched distance debt accumulate at every rung like interest on a loan. We previewed the mysteries that will not let us rest, including Voyager's true status and the Milky Way's true size. We also previewed the Andromeda question, and the expanding universe that turns horizons into prisons, even as it fills our telescopes with light. Next, we stop speaking in abstractions and start paying the bill. We will take real spacecraft speeds, real propulsion limits, and real mission timelines, and we will keep the assumptions visible. We will ask what it would cost to cross even the nearest interstellar gap without cheating physics, and what trade-offs the math demands. And we will see exactly when the universe stops being a place you can go and becomes only a place you can watch. Beautiful, vast, and indifferent. We leave the scale trap behind and rebuild our neighbourhood with a harsher ruler, one that does not care how our brains prefer to picture space. We measure the solar system the way it actually behaves, as delay, as travel time, as empty space that refuses to cooperate. Start close, where intuition still tries to negotiate and the sky still feels like a ceiling. Earth to Moon is about 1.3 light seconds, and that number is already a warning you can hear. In a clean studio, 1 second is nothing. In a conversation, it becomes a stumble. If you spoke to an astronaut there, every reply would arrive late, even with perfect gear and perfect attention. You would ask a question, wait, hear the answer, and realize you are always speaking to the past. Even the most ordinary exchange becomes a rhythm of pauses, like talking through a long tunnel. That lag is not drama, it is physics enforcing a speed limit on information. Nothing with mass can carry a signal faster than light, and even light needs time to cross space. Light time turns distance into a pause you must accept before you can act. It also turns every command into a prediction, because the situation changes while your signal travels. When you press a button on Earth, you're not touching the spacecraft. You're sending a suggestion that arrives later. The craft will obey in a future you cannot see yet. This is the first quiet lesson of spaceflight. Control is never direct, it is always delayed. Engineers learn to think in timelines, not in moments, because the universe meters out causality. In space, the present is local, and everything else is a report. Now push outward to the Sun, because the Sun is our first real baseline and our first honest gulf. Sun to Earth is about 8.3 light minutes, which means sunlight is always old news. The warmth on your face is a message that left the Sun before you decided to step outside. If the Sun changed, Earth would keep orbiting in ignorance for those minutes, following an older reality. That delay is small on a clock, yet enormous as a concept, because it means we never see the Sun now. Even our nearest star is a memory by the time it arrives. This is why distance in space is best understood as delay, not as a number on a map. Radio waves move at light speed, so every message is a time capsule sealed by geometry. Mission control does not steer spacecraft like a drone. It schedules actions and waits. The Deep Space Network is built around this truth, with giant dishes that listen more than they speak. In the desert heat of California, in the dry air of Spain, in the wide skies of Australia, antennas pivot slowly. They are not searching for a voice in the noise, they are catching a whisper that left hours ago. Near Earth, delay is small enough to feel like a technical detail, like latency on a phone call. Beyond the Moon, delay becomes a design constraint that shapes every procedure and every checklist. Beyond Mars, it becomes a psychological constraint, because urgency and helplessness arrive together. Communication is not the only clock that matters, because travel has its own cruelty, and it is not negotiable. Light crosses an astronomical unit in minutes, but rockets cross it in months, even when everything goes well. That mismatch is the heart of the solar system's true size. Earth itself shows the first trick, because we are already moving fast and still going nowhere in human terms. Earth orbits the Sun at about 30 kilometers per second, faster than a rifle bullet and steady as a metronome. Yet that speed is only enough to keep falling around the Sun, not to leave it. Orbital speed feels like freedom until you compare it to the distance it must cover, day after day without stopping. At 30 kilometers per second, you travel about 1,800,000 kilometers per day. That sounds huge until you remember the Sun is 150 million kilometers away. Even then, you are not approaching the Sun in any simple sense, because your motion is sideways. Orbit is a balance between speed and gravity, a perpetual miss that never becomes a hit. The solar system is full of these elegant compromises. Escape is different from orbit, because escape demands extra energy at the worst possible moment when gravity is strongest. You must climb out of Earth's gravity well, then reshape your path around the Sun with precision. Every kilometer per second you add cost, propellant, mass and mission options. This is why launch vehicles are mostly fuel tanks, and why space missions begin with a violent brief bargain. You spend most of your energy in minutes, then you coast for years on what you manage to buy. The rest of the journey is accounting. Typical deep space probes leave Earth fast by human standards, and slow by solar system standards, and the difference matters. Many cruise in the tens of kilometers per second relative to the Sun, sometimes more with gravity assists. Even then, the outer planets are not a quick trip. They are a calendar. Gravity assists look like cheating, but they are bookkeeping, a way to trade geometry for fuel. A probe steals a little orbital momentum from a planet, borrowing speed by passing through its moving gravity field. The planet never notices, but the spacecraft's schedule changes by years. The technique has a history as well as a math, because it turned impossible missions into possible ones. Voyager's grand tour depended on a rare alignment, and engineers built a route like a chain of swinging doors. Each flyby was a timed handshake with a moving world. Now we rebuild the map using light time, because light time exposes what diagrams hide. The moon is 1.3 light seconds away, so it is close enough for delayed conversation and careful teleoperation. The sun is 8.3 light minutes away, so even our star is not immediate. Visually, the scale is almost insulting because the inner solar system fits on posters like a neat clockwork. Yet the real map is a map of waiting, with empty intervals stretched between small, bright dots. The space between the dots is the story. Jupiter is the next shock because it is the first truly distant neighbour, and the first-time delay becomes unavoidable. Sun to Jupiter is about 43 light minutes, depending on where Earth and Jupiter sit along their orbits. A command sent now can arrive nearly an hour later, and the reply comes an hour after that. That round-trip delay breaks the fantasy of real-time control, even if your spacecraft is healthy and your plan is perfect. You cannot drive a rover on Jupiter's moons with a joystick from Earth. You must send sequences, trust autonomy, and accept that mistakes unfold before you can intervene. The delay also changes how you feel time, because it forces you to inhabit two timelines at once. On Earth, you watch screens update with old events, and you react to a world that has already moved on. In deep space operations, live is always a polite fiction. Neptune pushes the lesson into a different category of patience, because the delay becomes long enough to reshape a workday. Sun to Neptune is about 4.1 light hours, again depending on orbital positions and the slow dance of the planets. A round trip can be most of a working day, which turns troubleshooting into slow-motion crisis management. Light time also changes how you think about emergencies, because emergencies are time-sensitive by definition. A spacecraft can enter safe mode, spin, or lose lock while you wait for the first hint. By the time you understand the problem, the system has already lived through hours alone. Safe mode sounds gentle, but it is a kind of panic posture, a machine curling inward to survive. Instruments shut down, antennas search, heaters protect the core, and the mission pauses itself. The craft becomes conservative, because conservatism is what keeps it alive. This is why mission planning becomes choreography rather than steering, and why the planning rooms look like theatres. Engineers write scripts, test them, and upload them like sealed instructions carried by light. The spacecraft executes them in silence, then reports back what happened when the light finally returns. In the control room, the tension is not in the moment of action, but in the long wait afterward. You send the sequence, and then you can only watch the clock advance toward the time the answer can possibly arrive. The universe does not allow impatience to become speed. The solar system is also big in a quieter way, because most of it is nothing, and nothing is heavy. The planets are not lined up like beads. They are isolated islands in a vacuum sea. The emptiness is the dominant feature, and it is what makes travel expensive. Between Earth and the Moon, space is already empty enough to kill you quickly, because there is no air and no shelter. Between Earth and Mars, space is empty enough to erase any sense of proximity, because the background barely changes. Between Jupiter and Saturn, the gap is so large that a hole in a solar system could fit inside. We say the solar system is a family, but families live close enough to shout across rooms. Our planets do not shout, they whisper across hours of light time and years of travel. The only reason it feels familiar is that we learned the names as children. Now we build the solar system outward, not by orbit lines, but by consequences that accumulate with every extra AU. 1 AU is the step from Earth to Sun, and it is already a gulf that light needs minutes to cross. 5 AU is Jupiter's realm, where sunlight is weaker and the schedule is slower. At Jupiter, the sun is still bright, but it is no longer dominant in the sky the way it is here. Shadows deepen, temperatures fall, and solar panels become less practical without careful design. Even the lighting becomes a reminder that you have travelled far. At 30 AU, Neptune marks the edge of the classical planet list, not the edge of the system itself. Neptune's orbit is not a wall, it is a sign that the Sun's architecture keeps going. Beyond it, the solar system becomes a population problem rather than a planet problem. The Kuiper Belt begins as a region of icy bodies beyond Neptune, but it is not a neat ring you can draw with a confident hand. It is a broad, sparsely populated volume with structure, resonances, and gaps carved by gravity. Its objects are small, dark, and separated by distances that make collisions rare. Many of these bodies are coated with complex organics altered by radiation, materials that can look reddish and soot-like. They reflect little sunlight, so they hide in the glare and the darkness at once. Finding them is less like spotting rocks and more like detecting faint errors in the starfield. Pluto is the famous name, but Pluto is not a finish line and never was, even when it was called the ninth planet. Pluto is a signpost that tells us something exists out there and that our categories were incomplete. It is one member of a larger community of Kuiper Belt objects, many still undiscovered. Historically, Pluto's discovery in 1930 felt like closure, a final dot on a tidy map. For decades, textbooks treated it as the last step, the cold edge of the known. Then better surveys arrived, and the edge began to dissolve into a crowd. The scattered disk stretches the story further, because it is even less orderly and even more revealing. These objects have elongated, tilted orbits shaped by ancient migrations and gravitational kicks, especially from Neptune. They spend most of their time far from the sun, moving slowly through deep cold. Their paths are like long exhalations, arcing outward for centuries and then returning inward on schedules longer than nations. In the deep outskirts, sunlight is so faint that day is a technical term, not a feeling. The solar system becomes a dim laboratory of ice, rock, and time. When people imagine the Kuiper Belt, they often imagine a dense debris field, a place where spacecraft must dodge constant hazards. The reality is closer to a vast desert with occasional stones, separated by distances that mock the word belt. The danger is not impact. The danger is distance, because distance is what turns simple travel into long-term survival. Even the word belt can mislead, because it suggests a thin band like Saturn's rings, crisp and flat. In practice, it is a thick region with objects above and below the ecliptic plane. The solar system is not flat in the way textbooks imply, and its outskirts are especially three-dimensional. Light time keeps scaling as you go, and it keeps punishing impatience in the same calm way. Neptune at 4.1 light hours is still within the Sun's immediate communication sphere, if immediate is allowed to mean half a day. Yet it already forces a human team to work in delayed cycles, like doctors treating a patient by mail. Travel time is worse, because travel time is paid in propulsion and years accumulate consequences. A probe to Jupiter can take several years depending on trajectory and assists, even when the math is kind. A probe to Neptune can take a decade or more, and that is with careful planning and luck. Those years are not empty because spacecraft age and budgets change while the craft keeps coasting. Power sources decay, instruments drift, and software must remain reliable without updates or human hands. The mission must survive not only space, but also the slow erosion of attention back on Earth. A spacecraft is a sealed ecosystem of hardware decisions, and every decision becomes permanent once it leaves. A cracked solder joint, a stuck valve, a bit flipped by radiation. Any of these can become the story. Reliability is not a feature, it is the mission. Speed is the lever we want to pull, but it does not move as easily as we hope, because energy is expensive. Chemical rockets give strong thrust briefly, then coast for most of the journey, like a stone thrown hard into darkness. Ion engines can thrust longer, but with tiny acceleration that trades urgency for efficiency. That trade is not abstract, because tiny acceleration means months of gradual change, instead of minutes of dramatic change. You do not feel the push, but the trajectory slowly bends day after day until the numbers finally add up. The solar system rewards patience more than force. When we call a probe fast, we usually mean tens of kilometers per second, sometimes a bit more after assists. That is fast compared to airplanes, and slow compared to the distances involved, which is the cruel comparison. Against AU-scale gaps, even heroic speed becomes a long wait. This is the key contrast, because it reveals how the solar system defeats intuition without ever raising its voice. Earth's orbital speed is 30 kilometers per second, and it still takes a year to complete one loop. Our fastest probes can outrun Earth, and they still take years to reach the outer worlds. Distance is not a single obstacle, It is a stack of obstacles that multiply and interact. You must launch, escape, navigate, communicate, and keep functioning while nothing around you helps. The emptiness offers no refueling, no shelter, and no shortcuts. Light time also changes what exploration means, because it changes what presence means in the simplest human sense. If you cannot act instantly, you cannot truly be there the way your body expects to be. You can only send intentions ahead, then receive the consequences later. That is why, beyond the moon, real-time control breaks down in principle, not just in practice or budget. The moon is close enough that delay is tolerable for some tasks, especially slow, careful ones. Beyond that, the loop is too slow, and autonomy becomes the price of distance. Autonomy is not a luxury feature. It is a survival requirement written into the physics. A spacecraft must detect faults, protect itself, and continue the mission while Earth is still waiting for a first report. The farther it goes, the more it must behave like a small, lonely robot civilization. And autonomy has limits, because it is built from assumptions that may fail in unfamiliar conditions. Engineers try to anticipate failures, but the universe invents new ones with casual creativity. The craft must be cautious, because caution is the only substitute for rescue. The solar system also contains a deeper emptiness, because its outskirts are not a clean boundary you can point to. The sun's gravity reaches far, and its influence fades gradually, thinning like a voice across a field. The region beyond Neptune is not an edge, it is a transition into thinner and thinner membership. Pluto's demotion was never about disrespect, it was about measurement and about what we learned by counting. Once we found more objects like it, the category of planet could not hold without losing meaning. The lesson is that the solar system is not a tidy list. It is a continuum shaped by formation history, so we have rebuilt the neighbourhood with honest units, and the result is unsettling in a specific, measurable way. The moon is seconds away in light, but still distant in human reflex and human comfort. The sun is minutes away. Jupiter is nearly an hour away. Neptune is measured in hours. Those are communication delays, not travel times, and that distinction matters more than it first appears. Light time tells you how quickly reality can be known, even with perfect instruments. Travel time tells you how slowly hardware can cross the same space, even with brilliant engineering. When you combine them, you get the true texture of exploration, long periods of silence punctuated by delayed knowledge. You act, you wait, you learn, and then you act again with new uncertainty. The solar system trains you to accept that feedback is never immediate. Now we connect this chapter back to the central question, because the solar system is our training ground and our warning label. If even this small region overwhelms intuition, then interstellar space will not be forgiving. The universe does not care about our stories, it cares about limits. We have been told the universe is big, but we were not told what big does to planning and to responsibility. Big turns decisions into commitments you cannot revise quickly, because the consequences arrive late. Big turns rescue into impossibility, because help cannot arrive before the crisis ends. This is the moment where hope starts to change shape, not into despair, but into a harder kind of realism. Hope becomes less about heroic travel, and more about durable systems that can endure isolation. Hope becomes instruments that can wait, and messages that can arrive long after their senders are gone. Now we ask the simplest terrifying question, because it forces the numbers to become history rather than theory. How far have our farthest messengers actually gone, measured in AU, in light time and in years of travel? The answer will not feel like science fiction, it will feel like a receipt. Next, we stop speaking in abstractions and start paying the bill. We follow the trajectories we have already flown, and we measure what they imply about everything we dream of doing next. Voyager 1 is our protagonist because it is the farthest thing we have ever touched, a machine still moving long after its builders changed. It is also a reality check, because headlines turn a boundary into a destination, and the universe rarely respects our need for neat endings. In 1977, Voyager 1 leaves Earth on a chemical rocket, carrying a small nuclear heart that will slowly cool with time. The launch is a bright, violent moment, white exhaust, trembling steel, a rising needle of light, followed by an immediate quiet as space takes over. It launches into a solar system that looks familiar on posters and hostile in arithmetic, where distance is not scenic but punishing. The timing is not accidental. and the history matters because it shaped what was possible. NASA had noticed a rare planetary alignment that would let one craft visit multiple outer worlds with minimal fuel. The idea is old in principle, but new in practice. Use the planets as engines you do not have to carry. The mission is built around gravity assists, because fuel cannot buy everything you want, especially not speed at the edge. Jupiter and Saturn become moving machines, lending momentum through geometry and timing, as if the spacecraft borrows a fraction of a planet's orbital motion. In a flyby, gravity does not merely pull, it redirects, and in the right frame it can accelerate. The flybys are not detours, they are the only way the schedule closes, and the math is unforgiving. Each planetary encounter bends the trajectory and raises the speed without carrying extra propellant, trading careful navigation for enormous gain. The spacecraft threads through a three-dimensional target, where minutes matter and small errors compound into millions of kilometers. As Voyager approaches Jupiter, the visuals shift from starfield to a swollen disk with banded clouds and a bruised red storm. Instruments read radiation that would kill unshielded electronics, and engineers watch counters climb as charged particles slam the detectors. Even here, the solar system announces its hostility, not with drama but with numbers. Then Saturn, a planet that looks delicate but is heavy enough to rewrite a trajectory. The rings flash like a thin blade as the spacecraft passes, and the moons become moving landmarks in a clockwork scene. The encounter is also a decision point, because the mission cannot keep every option open. After Saturn, Voyager 1 is aimed outward, away from the ecliptic and away from return, and the camera of the mind tilts. The spacecraft becomes a long experiment in endurance, not a sprint. With fewer encounters and more time spent in darkness, the outer solar system is not empty, but it is sparse enough that emptiness becomes a dominant feeling. By the mid-2020s, Voyager 1 is on the order of 160 AU from the Sun, a number that sounds abstract until you picture it. 1 AU is the Earth, Sun distance, about 150 million kilometers, and Voyager has stacked that baseline more than 100 times. It is still tiny on a galactic map, yet it is already beyond the intuitive reach of human travel. Its speed is about 17 kilometers per second relative to the Sun, fast for engineering and slow for myth. It is faster than a rifle bullet and slower than the story we tell ourselves about interstellar as a word. The spacecraft is not racing into the stars. It is drifting outward on a long, steady line. We keep hearing that Voyager left the solar system, and the phrase sounds final, like a door closing behind it. The truth depends on what you mean by solar system, and what you think counts as an exit. In astronomy, definitions are not just semantics, they are models of what forces matter. If solar system means the planets, Voyager left decades ago, beyond Neptune's orbit and beyond the familiar orbit diagrams. Neptune is around 30 AU, and Voyager is far past that, in a region where sunlight is weak and the Kuiper belt thins. If solar system means the sun's plasma bubble, the story becomes technical and measurable. If solar system means the sun's gravity, Voyager has not left, and will not for ages, because gravity does not end at a line. It fades with distance and never truly turns off, and the sun's pull remains stronger than the galaxies for a very long way. Even a weak force, given enough time, shapes trajectories and keeps objects bound. So we need the real vocabulary, because the real boundaries are physical regimes rather than lines on a map. The heliosphere is the sun's wind inflated into space, a magnetic breath that pushes outward and drags the sun's field into a vast spiral. It is a bubble made by pressure, not by ownership. The solar wind is plasma, charged particles threaded with fields, streaming supersonically from the corona at hundreds of kilometers per second. Supersonic here is not about sound in air, but about faster than wave propagation in plasma, where disturbances cannot travel upstream. The wind carves a cavity in the local interstellar medium by pressure, not by permission. That cavity has structure, and it has layers that matter for instruments that can feel particles and fields. The first major boundary is the termination shock, where the solar wind slows abruptly as it begins to lose the pressure battle. It is a shock in the fluid sense, a sudden conversion of directed flow into heat and turbulence. The termination shock is not a wall you could hit, it is a change in flow and a change in physics. The wind goes from supersonic to subsonic, because it can no longer bulldoze the interstellar medium with momentum alone. Energy that was organized becomes disordered, and the plasma becomes hotter and more chaotic. Beyond that lies the heliosheath, a turbulent region of slowed solar wind, and the imagery becomes stormy rather than empty. It is a mixing zone where particles, fields, and instabilities pile up and churn like a wake behind a ship. Magnetic field lines twist, reconnect, and trap energetic particles in shifting pockets. Farther out is the heliopause, the boundary where solar wind pressure yields to interstellar pressure, and where the sun's wind stops dominating. Voyager 1 crossed that region in 2012, based on plasma and particle signatures that changed in a way instruments could not ignore. The density of plasma increased, and the population of solar particles dropped, while galactic cosmic rays rose. That crossing is real, and it is scientifically historic, but it is not the edge of the sun in any absolute sense. The heliopause is a plasma boundary, not a border of gravity, light, or meaning, and the difference matters. A plasma boundary can be crossed in a day, while gravitational influence fades across tens of thousands of years. The sun's photons keep going, thinning with distance but never stopping, and its gravity keeps binding objects far beyond the heliopause. Even the sun's magnetic influence extends in complex ways, because magnetic fields are carried by plasma flows and can reconnect with interstellar fields. The definitions remain debated because nature offers gradients, not fences. The myth is not that Voyager did nothing, because it did something extraordinary and measurable. The myth is that it arrived somewhere, as if space were a sequence of rooms with doors and plaques. It entered a new plasma regime, yet it remained inside the sun's broader neighbourhood, where the sun still sets the long-term rules. To understand that neighbourhood, we have to talk about the Oort cloud, a hypothesis built from comet orbits and from the geometry of surprise. It is a proposed reservoir of icy bodies, loosely bound and extremely distant, where comets can be nudged inward by passing stars and galactic tides. We do not see the cloud directly, we infer it from the way comets fall. The idea has a history, and that history is part of why it persists. In the early 20th century, astronomers noticed that some comets take so long to return that their orbits are barely bound to the sun. Jan Oort argued that a distant spherical reservoir could explain why long-period comets arrive from all directions, not just along the plane of the planets. The inner Oort cloud may begin thousands of AU out, and the outer Oort cloud may extend to 50,000 AU, where the sun's grip is gentle. Some estimates push toward 100,000 AU, approaching a light year, which is a distance that redefines near. At those ranges, a small nudge can change a comet's fate, because the binding energy is tiny. This is not a measured map like planetary orbits. It is an inference with uncertainty in competing models. We see long-period comets arriving from all directions, and we reverse engineer their source by reconstructing their inbound trajectories. But those trajectories are altered by planets, outgassing jets, and observational limits, so the reconstruction is never perfect. Uncertainty matters here because it changes the emotional claim of leaving home, and it changes the scientific claim too. If the Oort cloud is real and vast, then the sun's neighbourhood is not 30 AU wide, and it is not even 100 AU wide. It might be tens of thousands of AU wide, a region measured in fractions of light years. Our backyard may be a light year wide even before we count the nearest star, and that is a strange thought. We imagine the solar system as a tidy set of orbits. Then we learn it may have a faint, distant halo of debris. The sun's influence could be a long tail rather than a circle fading slowly into the galaxy. Voyager 1 at 160 AU would then be deep inside the sun's extended membership, still early in the outward journey. It would be like walking out of your house and declaring you left your country while you're still on your own street. The distance is impressive, but the scale is indifferent. Now we convert that into time, because time is what distance does to plans. At about 17 kilometers per second, Voyager covers roughly 3.6 AU per year, a pace that sounds brisk until you compare it to the sizes we are discussing. The number is steady and unforgiving, because the spacecraft does not get a second burst of speed. That is a useful number because it turns romance into a calendar, and it turns ambition into patience. It tells you how quickly the solar system stops feeling like a mission, and starts feeling like an era, where the people who began the story are no longer present. The spacecraft becomes a message from an earlier civilization of ourselves. At that speed, reaching 1,000 AU takes on the order of a few centuries, which is longer than most institutions survive intact. Reaching 10,000 AU takes a few millennia, longer than many civilizations have lasted, and longer than most languages remain recognizable. the spacecraft's journey becomes a timeline across empires, not across budgets. Reaching 50,000 AU takes roughly 10,000 years, and reaching 100,000 AU takes roughly 20,000 years, depending on definitions and trajectory. The exact number slides with reference frames and small gravitational tugs, but the scale does not change. The Oort cloud, if it exists as imagined, is not a destination for humans. It is a geological timescale. Now the gut punch, because light years are the unit where stories break and metaphors fail. 1 light year is about 63,000 AU, and Voyager is moving at a pace that makes that number brutal. The mind wants to compress the distance, but physics refuses to cooperate. At Voyager speeds, reaching 1 light year takes on the order of 17,000 years or more, even if nothing slows it down. That is longer than recorded history, longer than agriculture, longer than most written language, and longer than the idea of a nation-state. It is a span in which continents of culture can rise and vanish. The nearest star system is about 4.24 light-years away, and the arithmetic is merciless even before you add complications. At Voyager speed, that trip takes tens of thousands of years, closer to 70,000, and the destination itself is moving. Stars orbit the galaxy, and their relative positions drift. So aiming is never a frozen problem. Even if you argue about exact velocities and reference frames, the conclusion stays fixed, because the gap is simply too large. Voyager is not a starship, it is a drifting artifact with a timetable measured in epochs rather than lifetimes. It is a proof of reach, not a tool of migration. This is where the central question sharpens, because physics turns romance into accounting and then into philosophy. When we measure the universe honestly, we learn what big does to hope and to time, and we learn what it does to meaning. If a journey outlasts the traveller by a factor of 1,000, what does going even mean? Voyager also teaches a second lesson, because distance does not only attack travel, it attacks information itself. Distance attacks information because communication becomes a fight against geometry, noise, and the slow decay of hardware. The spacecraft can be alive and still unreachable, which is a different kind of loss. Voyager's radio transmitter is not shouting into space, it is whispering through the inverse square law, and the whisper gets thinner every day. Signal strength falls with the square of distance, so doubling the distance quarters the power at Earth. By the time the signal arrives, it is weaker than the background hiss of the universe. On Earth, the deep space network must use giant dishes and long integration times, and the visuals are almost monastic. A white parabolic antenna turns slowly against a blue sky, then against night, listening with patience rather than force. Engineers pull a coherent message out of thermal noise, cosmic noise, and the planet's own interference. That extraction is not magic, it is signal processing and careful timing, and it depends on stability. Receivers lock onto a carrier, track Doppler shifts, and integrate over time to build confidence in bits that arrive half-buried in randomness. The link is not a conversation, it is a ritual of measurement repeated across light hours. Power is the other clock, because Voyager runs on radioisotope thermoelectric generators, and the decay is relentless. Plutonium-238 decays with a half-life of about 88 years, which means the heat output falls predictably and permanently. Every year forces new choices about what to turn off, because the budget shrinks like a tightening fist. Instruments are shut down one by one to keep the spacecraft alive and talking, and each shutdown is a small funeral. The mission becomes triage, preserving a thin thread of telemetry over maximal science, because survival is now the experiment. What remains is a core set of sensors and the ability to point an antenna with precision. Data rates shrink because link budgets shrink, and because the spacecraft must conserve power for heaters and control systems. What returns is not a flood of images, it is a sparse stream of measurements, numbers that require interpretation and patience. The drama becomes subtle, hiding in changes of particle counts and magnetic field direction. Even pointing becomes a vulnerability, because the high-gain antenna must stay aligned with Earth across billions of kilometers. Attitude control depends on thrusters and sensors that were never designed for half a century of operation. When a thruster valve ages or a sensor drifts, the spacecraft's ability to look home becomes fragile. When a fault occurs, the delay and the fragility compound into danger, and the timeline becomes strange. A misconfiguration can silence the craft, and the fix must be guessed, tested, and sent into the past, because by the time you hear the problem, it is already hours old. Deep space operations feel like surgery performed through a long tunnel. This is the quiet terror of deep space operations, because you cannot touch what you built and you cannot improvise with your hands. You can only send instructions and wait, while the spacecraft lives alone in cold, with no rescue and no replacement parts. The emptiness is not poetic here, it is operational. Voyager's continued contact is therefore not a victory over distance, it is a temporary negotiation with physics and entropy. Every year is borrowed time, and the cost is reduced capability and rising risk, because aging hardware does not forgive optimism. The mission's longevity becomes a lesson in margins, redundancy, and careful restraint. Eventually, the transmitter will fall silent, not because it reached a destination, but because the energy budget closes and the last watts are spoken for. The spacecraft will keep flying, yet it will become unreachable, a moving fossil that no longer answers. The silence will not be dramatic. It will be a missing tone on a screen. That is the theme we need to carry forward, because it scales upward with every rung we climb. The universe does not only separate bodies, it separates causes from effects and messages from listeners, and it does so with calm consistency. Distance is not a villain, but it behaves like one when you have a human clock. So what did Voyager actually prove, beyond engineering brilliance and scientific return that reshaped textbooks? It proved that even our farthest probe is still local, still inside a region defined by the sun's long reach. It proved that leaving one boundary does not mean entering the galaxy in a meaningful way. Interstellar space begins as a plasma regime, while the sun's gravitational story continues, and that duality is the trap in the headline. We hear interstellar and imagine stars, yet the measurement refers to particles and fields. The heliopause is a scientific milestone, but it is not a narrative finish line. It also proved that the word leave is slippery, because nature uses gradients and overlapping domains of influence. We want edges, but space offers transitions, and transitions can be wider than human history. If your boundary takes centuries to traverse, is it a boundary or a region? Now we connect this back to the opening hook, because the hook was never about awe, it was about calibration. You were told the universe is big, but not what big does to every plan, and not how it changes the meaning of near. Big turns travel into inheritance, because the trip outlasts the traveller. Big turns communication into archaeology, because the message arrives in a different world with different assumptions. Big turns exploration into a question of institutions, not individuals, because continuity must survive politics, economics, and attention. You need continuity across generations, and continuity is a harder problem than propulsion. Voyager's myth is therefore useful, because it reveals our instinct to declare victory early and to stop measuring. We cross a boundary and treat it like a finish line, because the mind needs closure, and the news cycle needs a headline. The honest measurement refuses closure, and it keeps the ladder visible. Voyager crossed the heliopause, yet it did not exit the sun's neighbourhood in the deeper sense, and the deeper sense is the one that matters for travel. The deeper sense includes the Oort cloud, the long tail of bound objects, and the slow fade of dominance into the galaxy's background. It includes the fact that a light year is not far enough to feel free. Now we pivot outward, because the next rung is not a new spacecraft, and it is not a new press release. The next rung is the Milky Way itself, an object so large that even light needs 100 millennia to traverse it. If interstellar space begins only after a multi-decade journey, then the galaxy is the real verdict. We will ask what it means to cross a structure that defeats even photons in human terms, and we will keep the comparison honest. Next, we stop speaking in headlines and start speaking in crossing times, because time is the currency the universe demands. We will measure the Milky Way the way Voyager measured the heliosphere, by limits that do not care. We will keep the central question in view, because it is the only honest compass we have. When we measure the universe with real speeds and real physics, we learn what is possible and we learn what is not possible for bodies that must eat, sleep, and die. Measured honestly, the universe does not just dwarf us, it isolates us. Now we pivot outward, because the next rung is not a probe but a structure. The Milky Way is our true neighbourhood, and it does not fit inside instinct. From Earth, the galaxy looks like a milky band, a pale smear poured across the night. In dark skies it has texture, bright knots, smoky gaps, and a subtle bulge towards Sagittarius. What we see is not the galaxy's shape, but a perspective effect, because we are standing inside the disk. From inside, it's a rotating system with layers, patterns, and missing mass. It is also a system with gradients, metallicity, age, and gas density change with radius and height. Even the starlight changes character as you move outward, from crowded brilliance to sparse, cold darkness. We call it a spiral galaxy, but that label hides the lived reality. We are embedded in the disk, looking through dust, trying to map a city from one street. Every direction is a corridor of overlapping lights, and distance becomes a guess wrapped in statistics. Start with the architecture, because structure is the first clue to scale. The Milky Way has a thin disk, a thick disk, a central bulge, and a bar. These are not separate buildings, but overlapping components, each with its own kinematics, chemistry, and origin story. The thin disk is where most bright gas and young stars live. It is relatively flat, relatively cold in motion, and organized by rotation. Cold here means low random velocities, so stars move in orderly, nearly circular paths instead of chaotic plunges. In the thin disk, clouds of molecular hydrogen collapse into clusters, and massive blue stars ignite like brief flares. Their ultraviolet light sculpts the surrounding gas into glowing nebulae, while supernovae seed the medium with heavier elements. The thin disk is the galaxy's present tense, where the next generation keeps arriving. The thick disk is older and puffier, with stars on more tilted orbits. It is a fossil layer, hinting at early mergers and long dynamical heating. Those stars carry chemical fingerprints, lower metallicities, different abundance ratios that suggest rapid early star formation and turbulent beginnings. Thick disk stars also spend more time above the plane, where the sky would look different. From that vantage, the dust lanes thin and the spiral pattern becomes easier to imagine. The thick disk is a memory of violence, preserved in the slow wobble of stellar orbits. At the center sits the bulge, dense with stars and complex orbits. Through it runs a bar, a stretched concentration that channels gas inward. The bulge is not simply a sphere of old stars, but a crowded region where gravity forces stars into families of resonant paths. The bar matters because it is a machine for redistribution. As it rotates, it can torque gas clouds, driving them inward and feeding bursts of star formation near the center. In simulations, bars also help build boxy, peanut-shaped bulges, structures that look like geometry carved from starlight. Spiral arms are not rigid spokes, and they are not permanent walls. They are density waves and star-forming regions, patterns moving through a rotating disk. Stars drift in and out of the pattern, while gas compresses, cools, and forms new stars along the arm's leading edge. The arms matter to us because they shape where gas collects and where stars are born. They also matter because they are hard to trace from inside. Our view is like trying to sketch a hurricane while standing in its rain bands, with visibility changing by the minute. Dust blocks visible light across the plane, and the plane is where most of the story is. Those dust grains are tiny, silicates, carbon-rich particles, and icy mantles, yet they are efficient at scattering and absorbing optical photons. In visible light, the galaxy's midplane becomes a curtain, dark and deceptively solid. Our maps depend on infrared surveys, radio lines, and careful modelling. Infrared slips through dust better, revealing cooler stars and the glow of warm grains. Radio astronomy goes further, using the 21-centimetre line of neutral hydrogen to trace gas across the disk, even on the far side. But even those tools do not hand us a perfect blueprint. Distances must be inferred from parallax, standard candles, and kinematic models that assume how the galaxy rotates. A small error in distance becomes a large error in structure because everything is so far away. Above and around the disk is the stellar halo, sparse and ancient. It contains old stars, globular clusters, and streams from disrupted dwarf galaxies. Visually, it is almost nothing, just a thin sprinkling, but dynamically it is a record of the galaxy's long appetite. Globular clusters are especially telling because they are compact and old, often more than 10 billion years in age. They orbit like relics, some on plunging trajectories that cut through the disk. Their compositions and motions help reconstruct when and how the Milky Way assembled its mass. Those streams are evidence that the Milky Way is not finished assembling. The galaxy grows by eating smaller systems, and the leftovers remain as moving scars. A stream is not merely debris, It is a time-lapse photograph of gravity, stretched across tens of thousands of light years. We also infer a dark matter halo, far larger than the visible galaxy. It is not a cloud you can photograph, but a gravitational scaffold you can measure. The halo's presence is felt in the way stars move, the way satellites orbit, and the way the outer disk stays bound. Place the Sun on this map because location changes what you can know. The Sun sits about 8 kiloparsecs from the galactic centre, roughly 26,000 light-years. That distance is measured with modern astrometry, but it rests on a century of incremental improvements in calibration. Historically, our place in the galaxy was not obvious. In the early 20th century, debates raged about the size of the Milky Way and the nature of spiral nebulae. The Great Debate era reminds us that even the word galaxy once carried uncertainty, not confidence. That position is not central and not safely outside, but suburban. We orbit within the disk, between major arms, in a region shaped by both order and noise. Local space is not empty either. There are bubbles carved by ancient supernovae and clouds that drift like weather systems. A kiloparsec is about 3,260 light-years, and the unit is a warning. Even local galactic distances are already measured in thousands of years of light travel. When we talk casually about a few kiloparsecs, we are compressing epochs into syllables. Now we measure the size, because size is what turns a home into a prison. The Milky Way's disk diameter is commonly quoted around 100,000 to 120,000 light-years. That figure is tied to where the stellar density drops and where the gas disk thins. But it is not a hard border. That number sounds clean, but the edge is not clean. A galaxy does not end like a continent, because stars thin out gradually into darkness. The outer disk becomes a whisper, fewer stars per cubic light-year, more gaps, and more room for uncertainty. There is no single brightness threshold that nature agrees to call an edge. The disk fades, the halo continues, and different tracers give different boundaries. Young stars define one outline, old red giants define another, and neutral hydrogen can extend farther still. Some extended structures may push the stellar distribution farther out than the textbook disk. The halo and faint outer disk can stretch the effective size larger. Even the disk itself can warp, bending like a vinyl record left too close to heat. Subtle, but measurable. Even the word diameter can mislead, because the galaxy is not a flat coin. The disk has thickness, the halo is roughly spherical, and both are in motion. The thickness is not uniform either, because the disk can flare outward, becoming puffier at large radii. When we picture the Milky Way from above, we often imagine a crisp spiral emblem. The reality is messier, patchy star formation, arm segments, spurs, and interarm clouds. The galaxy is not drawn with ink. It is assembled from probability and dust-filtered light. Now we translate that size into crossing time, because time is what distance does to hope. Light itself needs about 100,000 years to cross a 100,000 light-year disk. Even that statement carries a quiet sting, because light is the fastest messenger the universe allows. A civilization does not travel at light speed, and it does not survive unchanged for 100,000 years. The crossing time is the first honest hint of isolation. Empires rise and fall in centuries, languages mutate in millennia, and biology drifts even when technology stands still. If you travelled at Voyager's speed, the galaxy becomes absurd. Tens of thousands of years to a nearby star becomes tens of millions to cross the disk. The numbers stop being adventurous and start being geological, like the slow rearrangement of continents. Even at a tenth of light speed, which is far beyond chemical rockets, the crossing is about 1 million years. The Milky Way is a city too big to walk. At that scale, a mission is not a voyage, it is an inheritance passed from generation to generation. And there is another trap hidden inside the word cross. The galaxy is not empty space with a destination sign, because the interstellar medium has hazards, radiation, dust impacts, and the long-term reliability of any engineered system. Over 1 million years, even small risks accumulate into near certainty. Now we count the residents, because population is part of the scale. Star count estimates often fall between about 100 and 400 billion stars. The range itself is a clue that our view is partial, like trying to count a city's lights from inside a fog bank. That range is not sloppy reporting, it is a measurement problem. We cannot simply count points of light from inside a dusty disk. We see a biased sample, because bright stars shout while faint stars whisper, and dust silences whole neighbourhoods. dust obscuration hides stars behind thick lanes of cold material. In optical light, whole regions are erased, and the missing stars must be inferred. When you look toward the galactic centre, the visible sky becomes crowded and then abruptly blank, as if someone dragged charcoal across the lens. Faint red dwarfs dominate by number, and they are hard to detect at distance. These low-mass stars burn slowly and dimly, surviving for trillions of years in theory. They are the galaxy's majority, yet they barely announce themselves beyond the local neighbourhood. Surveys have limits in sensitivity, sky coverage, and wavelength. Every catalogue is incomplete, and completeness corrections depend on assumptions. Astronomers must model what they cannot see, then test those models against the fragments that are visible. We also live in a biased location, because we are not above the disk. Our line of sight is long through the plane, and confusion blends stars together. In crowded fields, multiple stars merge into a single point, and the background becomes a bright, misleading haze. So astronomers model the luminosity function, the distribution of stellar brightness. They combine local counts with galactic structure models to estimate totals. They also incorporate stellar evolution theory, because a star's brightness depends on mass, age, and composition, not just distance. Those models are powerful, but they carry uncertainty in the faint end. Small changes in assumptions about low-mass stars can shift the total by billions. The uncertainty is not a failure of method, but a reminder that we are measuring a forest from within its trees. Now we weigh the galaxy, because mass is the deeper truth than star count. The Milky Way has baryonic mass in stars, gas, and dust, plus a much larger dark component. Mass determines gravity, and gravity determines what can remain bound across cosmic time. Baryonic mass is the matter we can see and touch in principle. It includes the stellar disk, the bulge, the gas in the interstellar medium, and remnants. It also includes compact leftovers, white dwarfs, neutron stars, and black holes, that add weight without adding much light. The gas is not a minor detail because gas is both fuel and messenger. Cold molecular clouds trace future star formation, while hot ionized gas reveals feedback from supernovae and stellar winds. In radio and X-ray light, the Milky Way becomes a layered atmosphere, not a simple disk. Total mass includes the dark matter halo, which dominates the gravitational budget. Order of magnitude estimates often land around 1 to 1.5 trillion solar masses. That implies that most of what holds the galaxy together is not the bright disk we romanticize, but an invisible framework. That number is also uncertain, because the halo extends far beyond the visible disk. The farther out you measure, the more the answer depends on what you assume. At large radii, you have fewer traces, longer orbital times, and more room for systematic bias. We estimate mass using the motions of stars, gas, and satellite galaxies. We use globular clusters, stellar streams, and the orbits of dwarf companions as test particles. Each tracer samples a different region of the potential, and each carries its own measurement noise and selection effects. We also use the escape speed near the Sun and the way it changes with radius. These methods converge, but not perfectly, because the halo is not directly seen. The halo may be slightly flattened, slightly triaxial or clumpy, and each shape changes the inferred mass. Now the key mystery, because it is the reason dark matter enters the story. The Milky Way's rotation curve stays flat at large radii, instead of falling as visible mass predicts. This is not a subtle anomaly, but a persistent pattern seen in many spiral galaxies, including our own. In a simple Newtonian picture, orbital speed should drop as you move outward. If most mass were concentrated in the bright disk, outer stars would orbit slower. The math is straightforward in plain language. Less enclosed mass should mean weaker gravity, and weaker gravity should mean slower orbits. But observations show stars and gas orbiting too fast far from the centre. The speed does not decline the way a visible-only galaxy would demand. Radio measurements of gas combined with stellar motions trace this flatness well beyond the bright spiral arms. This is not a small discrepancy you can ignore with better telescopes. It is a systematic mismatch between gravity and what we can account for in light. The mismatch persists even when we carefully inventory gas, dust, and faint stellar populations, and it forces a deeper explanation. So we infer an unseen halo, extended and massive, wrapping the galaxy. Dark matter becomes the simplest scaffold that holds the rotation curve together. Simplest does not mean simple. It means the fewest new assumptions that fit a wide range of gravitational evidence. We do not know what dark matter is, and that ignorance matters. It is not a detail, because it means most of the galaxy's mass is invisible to our senses. We can map its influence, but we cannot yet name its substance with laboratory certainty. The Milky Way becomes a character with a hidden skeleton. We live inside a structure whose dominant component does not emit, absorb, or reflect light. That is a profound inversion of intuition, because our brains evolve to trust what shines. Dark matter also shapes the galaxy's formation and stability over time. Without it, the disk's dynamics and the survival of satellites become harder to explain. In the early universe, dark matter's gravity likely gathered material into the wells where gas could cool and ignite stars. Yet dark matter is still a hypothesis with competing candidates and no direct detection. The evidence is gravitational, and gravity only tells you how mass behaves. It tells you nothing about whether the mass is a particle, a field, or something stranger that hides from our instruments. Now we return to motion, because the galaxy is not a static backdrop. The Sun is orbiting the centre at roughly 220 kilometers per second. That speed is measured relative to the galactic centre, after subtracting local motions and the Sun's own small, peculiar drift. That speed sounds fast until you see what it buys you. One full orbit, a galactic year, takes roughly 225 to 250 million years. The number depends on the exact distance to the centre and the local circular velocity, both refined as measurements improve. When the Sun last completed a lap, dinosaurs had not yet appeared. When it completes the next, no one can promise our species will still exist. The Milky Way's timescales make human history look like a brief flicker on a long exposure photograph. Our entire recorded history is a thin scratch on one segment of that orbit. The Milky Way's clock is not a human clock, and it never will be. Even the rise and fall of civilizations is too fast to register against the slow turning of the disk. The orbit is also not perfectly circular, and the environment changes as we move. We drift through spiral structure, through varying gas density, through changing radiation fields. As we pass through different regions, the sky's background glow and the frequency of nearby supernovae can change, subtly altering the local cosmic weather. The galaxy's gravity field is lumpy, shaped by arms, the bar, and passing satellites. Over long times, these perturbations heat stellar orbits and reshape the disk. Stars gradually gain random motion, thickening the disk and blurring the clean, idealized rotation we draw in diagrams. Even the Sun's path is a slow migration, not a fixed address. Stars exchange angular momentum, and the disk can mix populations across radii. Over billions of years, a star can drift inward or outward by thousands of light years, carrying its chemical signature into new neighborhoods. So the Milky Way is not only large, it is alive in a dynamical sense. It is a rotating ecosystem of matter, energy, and time. The present structure is a snapshot, one frame in a long film of accretion, feedback, and gravitational rearrangement. Now we connect this to the central question, because scale is never just awe. When we measure the Milky Way honestly, we see what it does to travel, to rescue, and to continuity. The distances are not merely impressive, they are operational constraints that shape what is possible. To cross the disk is to commit to times longer than civilizations endure. To communicate across it is to accept messages that arrive after cultures have changed. Even if a signal remains intact, the context that gives it meaning may have evaporated by the time it is received. Even if propulsion improves, biology still pays the bill in lifespan and fragility. The galaxy forces any living traveler into generational missions or post-biological solutions. The question becomes less about speed and more about identity. What counts as us after centuries of transit? And the galaxy is only one island, not the ocean. The Milky Way's size is already enough to isolate its own neighborhoods from each other. If there are other intelligences in the disk, they may be separated not by hostility, but by indifferent geometry. Now we sharpen the isolation with a final comparison inside the galaxy. The Sun is 26,000 light-years from the centre, which is already a 26,000-year message delay. Even a perfectly aimed beacon is a letter sent to a future that cannot write back in the same era. A signal to the far side of the disk would take on the order of 100,000 years. Any reply would arrive after 200,000 years, if anyone remained to answer. What does diplomacy mean when every exchange spans longer than the lifespan of most species, and longer than many ecosystems persist? That is what big does to conversation, and conversation is what coordination requires. A galaxy-spanning civilization would not think in years, but in epochs. Its institutions would need to be more like geology, slow, resilient, and tolerant of long silence. So we treat the Milky Way as a city of stars, but it is a city without streets. It is a city where every neighbourhood is separated by lethal vacuum and ancient delay. The lights look close in the sky, yet each is a distant sun, surrounded by darkness that resists connection. Now we admit what we still cannot see, because mystery is part of honest measurement. We cannot map the far side of the bar with perfect clarity through dust. Even with infrared and radio, the inner galaxy remains crowded, confused, and difficult to untangle into distinct structures. We cannot inventory every faint star, every cold cloud, every compact remnant. We cannot yet draw the dark halo's exact shape, or its substructure, with confidence. Some uncertainties will shrink with better surveys, but some are intrinsic to being embedded inside the system we measure. We suspect the halo is filled with clumps and streams of dark matter. Those clumps may influence stellar streams and the stability of the disk. If a stream shows a gap or a kink, it may be a gravitational footprint, evidence of an invisible passerby. We also suspect the Milky Way's spiral pattern is more complex than a simple four-arm diagram. Different traces suggest different arm segments and different pitch angles. Young massive stars, ionized gas regions, and massa measurements do not always agree, because each tracer highlights a different phase of the galactic ecosystem. Even the galaxy's mass estimate depends on how far the halo extends and how satellites move. The uncertainty is not ignorance of basics, but limits of measurement from inside. We are doing cartography while riding the spinning platform, and the platform itself is evolving. Yet the outline is clear enough to be terrifying. The Milky Way is vast, structured, and dominated by unseen mass, and we are a small orbiting point within it. The more precisely we measure it, the more it resembles a machine built for timescales we cannot inhabit. Now we build the next rung, because the ladder does not stop at our island. If the Milky Way is our city, the next question becomes inevitable. How does our island compare to the nearest great rival in the dark? And what does that comparison do to any dream of leaving our galaxy at all? Andromeda is not a mythic smudge in the sky. It is a full spiral galaxy, close enough to threaten our sense of distance. Its modern distance is about 2.5 million light-years, give or take refinements in calibration. That number is small on a cosmic ladder, and enormous on any human clock. The value itself is the endpoint of a long argument between methods. Cepheid variables, red giant branch stars, and other standard candles each contribute rungs. Each rung carries its own systematics, metallicity, dust, crowding, and each correction nudges the final number. Under truly dark skies, Andromeda is the farthest object most humans can see unaided. The light that reaches your retina left before our species had agriculture, cities, or written memory. Imagine the scene as a visual, a quiet horizon, a cold band of the Milky Way, and then that pale oval. It is not bright like a planet. It is a soft stain, barely there, yet it is an entire galaxy. Its apparent size is another trap because the eye expects small things to be far away. The bright core looks modest, yet the galaxy's full span covers several moon widths when you include faint outskirts. The reason is partly biological, not astronomical. Human vision is tuned for contrast, so we notice the core where the surface brightness is highest. The outer disk and halo fade below the threshold, even though they occupy more sky. We have been trained to picture galaxies as neat disks with clean edges. Andromeda refuses that simplicity, because the disk is only the bright centre of a much larger structure. Even the word edge is a convenience. In real galaxies, starlight thins out gradually, and the boundary depends on what you measure. If you count bright young stars, you get one radius. If you trace old red giants, you get another. Start with the disk, because disks are what posters show and what intuition trusts. Andromeda's stellar disk is often quoted around 200,000 to 220,000 light-years across, larger than the Milky Way's commonly cited disk. That comparison is not a single number, because both galaxies have edges that fade. Different tracers draw different borders, and every border depends on how deep you can see. Some measurements emphasize the star-forming ring, where gas and dust organize into spirals. Others follow the diffuse glow of older stars, which can extend well beyond the obvious arms. In deep exposures, the disk looks less like a plate and more like a foggy continent. A vivid way to picture it is to imagine the bright core as a city at night. The suburbs extend farther than you expect, and beyond them are scattered lights. The map keeps expanding as your eyes adjust and your camera integrates. Now we widen the frame, because the disk is not the whole galaxy. Around Andromeda is an extended stellar halo, thin in brightness and vast in reach. Halos can stretch hundreds of thousands of light-years from the centre, and some measurements imply even farther. The halo is not a wall, it is a gradient of ancient stars, globular clusters and debris. Those halo stars are typically old and metal-poor, which is a plain language way of saying they formed early. Many were not born in the main disk at all. They were donated, stripped from smaller galaxies that wandered too close. Globular clusters help mark this territory because they are bright and compact. They orbit like fireflies around a lantern, and their motions encode the mass distribution. Each cluster is a fossil, preserving chemistry from an era when galaxies were still assembling. This is where the word collision starts to mislead, because overlap begins long before impact. Two halos can interpenetrate conceptually, while disks remain far apart, trading stars and dark matter through tides. Tides are not just ocean metaphors, they are differential gravity, pulling harder on the near side than the far side. Over millions of years, that gentle imbalance can unbind a dwarf galaxy and smear it into a stream. The Milky Way has its own halo, and it is not small. When you compare halo to halo, the gap between galaxies feels less like an empty gulf and more like a contested region. That is the first tension Andromeda introduces. It is close enough that the outskirts of two giant systems can be discussed in the same breath. In a wide visual, the local group stops looking like dots on a chart. It starts looking like two overlapping weather systems, each with a bright centre and a vast, dim envelope. The emptiness between them becomes structured, thinly but meaningfully. Now we measure mass, because mass decides fate more than starlight does. Andromeda is often estimated comparable to, or somewhat more massive than, the Milky Way. Typical totals land around 1 to 2 trillion solar masses for each system, with wide error bars. The uncertainty is not laziness. It is the cost of weighing something you cannot put on a scale. Most of that mass is not in stars or even in gas. It is in dark matter, inferred from gravity rather than seen directly. The visible galaxy is the frosting, and the halo is the cake, large, heavy, and mostly unseen. Different methods answer different questions, and they do not always agree. Each method is a model of gravity, built from limited traces and imperfect assumptions. One approach uses satellite motions as test particles in a gravitational field. If satellites orbit fast at large radii, the halo must be heavy enough to keep them bound. The logic is simple, even if the data is not. Velocity tells you about the depth of the gravitational well. Distance tells you how far out that well still holds sway. Together they sketch the invisible mass profile, but satellites are not ideal probes because their orbits are not fully known in 3 dimensions. Proper motions are hard at these distances, and small errors become large changes in inferred mass. A satellite can also be out of equilibrium, especially if it is falling in for the first time. If you mistake an infalling object for a settled orbiter, you can overestimate the mass. If you miss a fast satellite entirely, you can underestimate it. Another approach models the halo profile itself, assuming a shape and concentration motivated by cosmological simulations. Change the assumed profile, and the same data can imply a different total mass. Simulations often favour a cuspy inner density, but real galaxies can be messy. Baryonic physics, gas cooling, star formation, feedback can reshape the inner halo. A small change in concentration can move a trillion solar mass estimate by a large fraction. A third approach uses the local group timing argument, treating the Milky Way and Andromeda like two bodies that separated with cosmic expansion, then slowed and turned around under gravity. The timing argument constrains the combined mass, then divides it with additional assumptions. Historically, this idea is part of a broader shift in cosmology. Once galaxies were recognized as island universes, the next question was how they moved. The timing argument is a relic of that era, elegant, approximate, and surprisingly informative. Each method has its own hidden dependencies, and the answers can shift as data improves. The result is a range of plausible masses, not a single verdict. Yet the broad message is stable. Andromeda is not a lightweight neighbour. It is a peer, and possibly the heavier one. Now we count stars because star counts are the emotional currency of scale. Andromeda is commonly quoted around 1 trillion stars, with high uncertainty and strong dependence on modelling. That number is not a direct census, because we cannot resolve every star across the whole system. We infer totals from brightness distributions, stellar populations, and assumptions about faint stars. Astronomers start with what they can measure, integrated light and resolved star fields in selected regions. They then extrapolate using the luminosity function, which is a statistical description of how many dim stars accompany each bright one. The faint end matters because dim stars are numerous. Andromeda may host more stars than the Milky Way because its bulge is larger and more prominent. A larger bulge implies more old stars packed into the centre and a different early history. Visually, the bulge is the bright nucleus you notice first. In long exposures, it looks like a glowing egg yolk embedded in a disk. That central light is not just beauty, it is mass in motion, and it hints at ancient upheaval. Merger history matters because mergers build bulges and thicken disks. A galaxy that ate more companions earlier can end up with more stars in a dense central component. Major mergers can scramble stellar orbits, turning a thin disk into a puffier structure. Even minor mergers repeated over time can heat the disk and feed the halo. The result is a galaxy that carries its past in its shape. But even here, the uncertainty is part of the story. Star counts depend on how you correct for dust, crowding, and the faint end of the luminosity function. Dust is not evenly spread, and it hides stars in some lines of sight. Crowding blends many stars into one pixel, especially near the core. Distance turns individual suns into a statistical glow, and the model becomes the measurement. The Milky Way's star count is uncertain because we are inside it. Andromeda's star count is uncertain because we are far outside it, and distance turns detail into statistics. Now we look at satellites, because satellites are the fingerprints of a galaxy's past. Andromeda has a rich system of dwarf galaxies, globular clusters, and extended companions. Some satellites are bright enough to be famous, and others are so faint they were found only with modern surveys. The census keeps growing as detection limits improve. This is a quiet revolution in observational astronomy. Wide-field digital surveys can comb huge areas for tiny overdensities of stars. What once looked like empty sky becomes populated with fragile, low-luminosity systems. Satellites are not just companions, they are future meals, and some are already half-digested. The evidence is written in stellar streams, long ribbons of stars pulled from disrupted dwarfs. Streams are not decorations, they are crime scene tape, marking where gravity tore something apart. In a visual montage, these streams look like faint brushstrokes around the galaxy, curving and looping in ghostly arcs. They are so dim that they barely rise above the background, yet they can wrap around Andromeda like shredded silk. A stream preserves orbital information, stretched out over time. Its path traces the potential it moved through, and its gaps and kinks can hint at invisible structure. Those gaps can be caused by encounters with dark subhalos, clumps of dark matter predicted by cosmological models. If a stream is a taut ribbon, a passing mass can punch a subtle hole. The stream keeps the memory, even when the perturber is invisible. In Andromeda, multiple streams and substructures suggest a violent assembly history. The halo is laced with debris, implying past mergers that left scars still visible today. This is a direct callback to the Milky Way's own halo streams, now seen in a neighbouring system. The pattern repeats. Big galaxies grow by eating, and the leftovers remain as evidence. There is a historical echo here as well. A century ago, Andromeda was photographed as a nebula, and its true nature was debated. Today, we read its outskirts like a forensic report because the tools finally match the scale. Now we connect this to the central question, because scale is never just awe. If two galaxies are separated by 2.5 million light-years, the travel problem becomes brutally clear. Even at 1/10th light speed, a hypothetical intergalactic ship needs about 25 million years to cross that gap. Biology does not negotiate with that timeline, and civilizations rarely survive unchanged for millennia. Even if propulsion was solved, the environment is not friendly. Intergalactic space is thin but not perfectly empty, and high-energy cosmic rays are relentless. Over millions of years, shielding becomes not a feature, but a foundational requirement. Communication is also trapped by delay. A message sent today reaches Andromeda in 2.5 million years, and any reply returns after 5 million years. That is not conversation. That is archaeology performed in real time, with the sender and receiver separated by evolutionary distance. It forces an uncomfortable question about meaning. What does it mean to contact a place when the receiver has had millions of years to change? At that scale, even a stable civilization becomes a hypothesis. Andromeda therefore becomes a mirror held up to our ambitions. It is the nearest large galaxy, and it is still effectively unreachable for bodies that must live and die. Yet Andromeda is not merely distant, it is approaching. The radial velocity is about -300 kilometers per second relative to the Milky Way, meaning it is coming toward us along the line of sight. That number is measured from Doppler shift, and it is one of the cleanest facts in the story. Spectral lines act like barcodes, and their shifts are precise. When lines move toward the blue, the source is approaching. When they move toward the red, it is receding. Andromeda's blue shift is a rare local exception to the universe's general expansion. But approach is not the same as collision, and this is where older narratives overreached. To know the future, we need the sideways motion too, not just the head-on component. Proper motion measurements are difficult at 2.5 million light-years because the angular drift is tiny. Modern astrometry has improved the constraints, but the uncertainty still matters for the ending. To appreciate how tiny, imagine watching a distant lighthouse from across an ocean. It can move, but the change is smaller than the thickness of a hair at arm's length. That is the scale of the measurement challenge. Earlier headlines treated the merger as guaranteed and the date as fixed. Newer data suggests a range of outcomes, from a direct collision to a near miss followed by a later merger. The physics still points toward interaction, because gravity binds the local group and drains orbital energy through dynamical friction. Two massive halos moving through each other create wakes in dark matter, and those wakes steal momentum. Dynamical friction sounds gentle, but it is cumulative. A moving mass gravitationally focuses surrounding particles, leaving an overdense wake behind it. The wake pulls backward, and the orbit slowly decays, an invisible braking system written into gravity, but the exact choreography depends on the transverse velocity and on the mass distribution in both halos. Change those inputs, and the timeline shifts by billions of years. Even the presence of other local group members can matter at the margins, because gravity is not a two-body story. The Milky Way's satellites, Andromeda's satellites, and the diffuse background all add small tugs. Over deep time, small tugs accumulate. Now we convert that into time, because time is what distance does to plans. The often quoted merger timescale is on the order of 4 to 5 billion years, but the uncertainty is large enough to change the story's tone. 4 billion years is not a countdown you can feel. It is longer than complex life has existed on land, and it is longer than the sun has left before it changes the rules. By then, Earth's environment will be shaped by solar evolution as much as galactic dynamics. The sun will brighten, oceans may diminish, and the habitable zone will shift. The Andromeda encounter becomes a cosmic backdrop to a much nearer deadline. So why does Andromeda feel like looming fate? Because it is the nearest proof that galaxies are not isolated islands forever, even when the distances look impossible. Andromeda makes the local group feel small, like a room with only a few heavy objects. In that room, gravity eventually forces encounters, even if the schedule is written in deep time. In simulations, the future is both dramatic and slow. Disks distort, tidal tails fling stars outward, and the cores spiral together. The sky would change over millions of years, subtle in a lifetime, overwhelming across epochs. Now we sharpen the comparison, because the Milky Way is our baseline and Andromeda is the rival. Andromeda's disk appears larger, its bulge appears heavier, and its halo shows extensive merger debris. The Milky Way is not the quiet one either, as Gaia has revealed our own past mergers. But Andromeda's visible substructure suggests a particularly active history, and perhaps a different balance of growth. A galaxy's present appearance is a compromise between orderly rotation and accumulated disruption. Andromeda looks orderly at first glance, then increasingly scarred as you push deeper. That layered impression is the clue. Calm on the surface, turbulent underneath. Mass still decides the final scene, and mass is still uncertain. If Andromeda is significantly heavier, it dominates the barycenter and pulls the encounter into a more decisive merger. If the masses are closer, the dance is more symmetric, and the outcome depends more sensitively on sideways motion. The uncertainty is not a footnote. It is the difference between inevitability and probability. Now we return to the definitional trap from earlier chapters, because words can hide the real boundary. We said Voyager left the heliopause but not the Sun's gravitational neighbourhood. In the same way, we say Andromeda is far, but the relevant boundary is not distance alone. The relevant boundary is what can be crossed by matter, by information, and by institutions that must persist. Intergalactic space is not just empty, it is a timescale barrier, and it makes biological travel feel like a category error. Andromeda also exposes a second boundary, the halo boundary, where galaxies already begin to touch in a dynamical sense. The halos are the real interface, and they are mostly dark. This is the quiet horror of modern cosmology. The most important parts of the encounter are invisible, because the dominant mass is dark matter. We can map the consequences through streams, satellite motions, and simulations. We cannot watch the main event directly, because the main event is gravity acting through unseen mass. That invisibility changes the mood of the story. The brightest parts of both galaxies are almost irrelevant to the accounting. The future is negotiated in the dark and the visible disks are passengers. Now we build the next rung because the ladder does not stop at our island. Andromeda is the nearest great galaxy, and it is still a multi-million light-year gulf. If the nearest neighbour is already beyond practical reach, then the wider universe becomes a field of unreachable ghosts. The expansion of space will push most galaxies beyond any future contact, even with perfect propulsion. At some point, the observable universe and the reachable universe diverge. We may see countless galaxies, measure their redshifts and map their history, yet never touch them. Andromeda is the nearest reminder that visibility is not access, so we end this chapter with a question that restores the tension. Andromeda is approaching, but are we truly on a collision course, or did older data turn a probabilistic future into a certainty? Next, we follow the measurement forward, because the honest story is never the headline. We ask what the local group's future really looks like, and what it implies for any civilization dreaming beyond its home galaxy. Andromeda is approaching, but approach is not a verdict, because motion has more than one direction. The local group's future hinges on one missing piece of motion, and that missing piece hides in angles too small to feel real. To predict the encounter, we need two velocities, not one, and we need them in the same three-dimensional frame. We need the radial velocity coming toward us at roughly 110 kilometers per second, measured along our line of sight. We also need the tangential velocity, the sideways drift across the sky, and that is the hard one. Radial velocity is generous to observers because physics gives us a clean handle and a clean translation. Spectral lines shift, and the Doppler effect turns light into a speedometer, with atomic transitions acting like ticks on a ruler. In practice, astronomers compare the observed wavelengths to laboratory standards, then correct for Earth's motion and the Sun's motion. For Andromeda, the line-of-sight approach is measured with high confidence, and it anchors every model. Even that confidence has a history, because it rests on a century of spectroscopy and calibration. The earliest measurements of galaxy redshifts made expansion famous, yet Andromeda stood out as a nearby exception. Its blue shift was a clue that gravity can overwhelm cosmic expansion on local scales. That clue still matters, because it tells us the local group is bound. Tangential velocity is stingy, because distance turns motion into tiny angles that almost refuse to exist. At 2.5 million light-years, even tens of kilometers per second become microarcseconds per year, a drift smaller than a pixel's whisper. The measurement is like tracking a coin's drift on the moon from Earth, using a ruler made of photons. It is also like timing a glacier's creep with a stopwatch that jitters. This is the same definitional trap we met with Voyager, where words tempt us into false finality. We said it left the heliopause, then admitted gravity still holds it for far longer than any mission lifetime. Here we say Andromeda is coming, then admit the sideways component decides whether coming means impact. A single missing vector component can turn a collision into a near miss, while headlines keep the simpler story. Now we translate that into method, because method is what turns suspense into science. Proper motion is angular change on the sky, measured against a reference frame that must itself be stable. Parallax is the apparent shift from Earth's orbit, and it sets distance for nearby stars with pure geometry. Combine distance with proper motion, and you get tangential speed, which is the sideways velocity we cannot directly feel. Parallax sounds simple, yet it is a triumph of scale, because the baseline is only 2 astronomical units. The angle is half the annual wobble, and the numbers are often measured in milliarc seconds or less. For nearby stars, that wobble is clear enough to separate from their own motion across the sky. For Andromeda, the parallax is effectively 0, so the distance must come from other methods. That distance too has a lineage, because Andromeda helped define the cosmic distance ladder. Cepheid variables, with their period, luminosity relation, were used to show it lay far beyond the Milky Way. Later, the tip of the red giant branch and other standard candles refined the estimate. The distance is not the main uncertainty here, but it sets the scale that converts angles into kilometers per second. Gaia is the instrument that made this chapter possible, because it was built to measure angles as if the sky were a laboratory. It measures positions, parallaxes, and proper motions for more than 1 billion stars, repeatedly and systematically. It repeats the sky again and again, building a time baseline that turns tiny drifts into data. The spacecraft spins, the fields of view sweep, and the same stars return like clockwork. Visually, Gaia's work is quiet and relentless, like a lighthouse that never stops rotating. Imagine the satellite tracing great circles, its detectors catching starlight for seconds at a time. Each pass records a position, then another pass returns months later, and then again. The power is not in one snapshot, but in the accumulation of many. Gaia's power is not one perfect measurement, but a global solution that treats the whole sky as one linked problem. It solves for spacecraft attitude, detector geometry, and star parameters together, because each depends on the others. It builds an inertial-like reference frame by tying stellar motions to distant quasars, which are so far away their proper motions are effectively 0. In that frame, the Milky Way's internal motions become a map of rotation and streaming. That reference frame is an achievement in itself, because the spacecraft is not rigid in the way a textbook assumes. Thermal changes flex the structure, radiation slowly alters detectors, and the scanning law imprints patterns into the data. Gaia's pipeline models these effects, then iterates until residuals shrink to the microarcsecond level. The result is a catalogue that is both an atlas and a time machine. But Gaia does not magically resolve Andromeda's disk star by star, because distance and crowding conspire against it. At Andromeda's distance, most individual stars are too faint and too crowded, blending into a luminous texture. Even when stars are detected, systematics can mimic motion at the microarcsecond level. The galaxy's own internal motions also smear the signal, because its stars orbit its centre at hundreds of kilometers per second. So the trick becomes statistical rather than individual, and statistics becomes a kind of telescope. Astronomers use ensembles of stars or specific bright traces and average down random errors. They also use background galaxies and quasars as fixed points, then measure Andromeda's bulk drift against them. The goal is not to track one star, but to extract a collective drift from a crowded field. In a visualization, the field becomes a layered stage with different depths. Foreground Milky Way stars slide across the frame, while distant quasars sit nearly still like pinned lights. Andromeda's stars, in between, carry both internal rotation and the subtle motion of the whole galaxy. The analysis tries to subtract the internal swirl and keep the faint translation. This is where the story reopens, because the uncertainties are not just noise that averages away. Systematic errors can come from scanning patterns, color-dependent shifts, and crowding biases, and these do not cancel cleanly. A tiny unmodelled bias can flip a tangential velocity from near zero to significant. When the signal is so small, the instrument's personality becomes part of the measurement. Colour matters because detectors do not treat all photons equally. A red star and a blue star can land slightly differently on the focal plane, and that difference can masquerade as motion. Crowding matters because blended images shift their centroids as the scanning direction changes. Even the background fixed galaxies have structure that complicates their centroids. Before Gaia, the collision narrative hardened into certainty, partly because the public likes a clean countdown. Hubble era and early HST proper motion studies suggested a small tangential component, consistent with a near head-on approach. If sideways motion is near zero, gravity does the rest, and a direct merger feels inevitable. The phrase "Milky Way will collide with Andromeda" became a kind of cosmic proverb. But small was always a conditional claim, built on limited baselines and difficult calibrations that pushed instruments to their edge. The HST measurements were heroic, but they were measuring a drift smaller than the width of the instrument's own uncertainties. The baseline spanned years, not decades, and the reference sources were few. The headline became firmer than the data, because certainty is easier to narrate than error bars. Gaia-era analyses refined the reference frame and expanded the baseline, but they also exposed fragility in the inference. Different selections of stars, different background calibrators, and different treatments of systematics produce different tangential estimates. One team's careful cut can become another team's hidden bias, because the data are rich and the choices are many. The result is not one future, but a family of futures. The family is constrained, not chaotic, and that distinction matters for how we imagine it. The radial approach is real, and the galaxies are close enough to feel each other strongly, yet the sideways motion is the hinge, and the hinge is still creaking. When the tangential velocity shifts by a few tens of kilometers per second, the closest approach can shift by tens of kiloparsecs. Now we widen the frame, because the encounter is not a two-body problem in empty space. The Milky Way and Andromeda move inside a gravitational family, and families are never simple. Other masses tug, torque, and reshape the orbit over billions of years. The local group is a small ecosystem of gravity, with satellites acting like moving weights on a mobile. Start with Triangulum M33, because it is not a bystander and never was. M33 is massive enough to perturb Andromeda's motion and absorb angular momentum during close interactions. Depending on its orbit, it can hasten a merger, delay it, or change the geometry of the first pass. In some scenarios, M33 itself may merge with Andromeda first, altering Andromeda's mass distribution before the Milky Way arrives. In a visual sequence, M33 appears as a smaller spiral, trailing faint streams like smoke. Its orbit is not a neat circle, but a long, slow curve, shaped by Andromeda's halo. When these halos overlap, the gravitational bookkeeping changes and the future path shifts. The local group's choreography is written in these subtle exchanges. Then consider the Large Magellanic Cloud, because it is heavier than we once assumed and closer than we like to remember. A more massive LMC shifts the Milky Way's center of mass and adds a moving gravitational pull. That changes the inferred Milky Way, Andromeda relative motion, and it changes the predicted encounter. It also means our own galaxy is not a fixed platform, but a system being tugged. The LMC's mass matters because it is not just a bright patch in the southern sky. It carries dark matter, and it drags a wake through the Milky Way's halo as it falls inward. That wake can torque the halo and slightly reorient the Milky Way's disk over time. When we measure Andromeda's motion, we must remember we are standing on a ship that is itself turning. The dark matter halos matter even more than the visible disks, because most of the mass is invisible and extended. Their total masses set the depth of the gravitational wells, and their outer reaches overlap before any starlight touches. Their shapes and concentrations set how dynamical friction drains orbital energy. In simulations, halos are the first to meet and the last to settle. Dynamical friction is the quiet engine of merging, and it sounds like a metaphor because it is so intangible. A massive body moving through a sea of dark matter creates a gravitational wake, an overdensity trailing behind it. The wake pulls backward, and orbital energy leaks away into the halo's random motion. In plain terms, the orbit loses speed because it stirs the dark matter like a spoon in thick liquid. But the strength of that braking depends on assumptions that are still under debate. If halos are more extended, friction acts earlier and longer, and the orbit shrinks more efficiently. If halos are less massive or differently shaped, the decay can slow, and the first pass can be wider. Even the distribution of subhalos can change the effective drag over time. Halo shape is not a cosmetic detail, because it changes the orbit's precession and the direction of torques. A spherical halo yields one trajectory, while a flattened or triaxial halo yields another, with different pericenter distances. Substructure and clumps can add stochastic kicks over long times, nudging the path like small taps on a pendulum. Over billions of years, small nudges can accumulate into meaningful shifts. This is the same cartography limit we faced inside the Milky Way, where we infer the halo from traces and streams. We do not see dark matter directly, so we map its influence through stellar motions and satellite dynamics. We can measure its pull, yet we still debate its profile, its asymmetry, and its outer boundary. The halo is the stage, but the stage is dimly lit. Now we return to what must be known, because prediction is only as good as inputs and priors. We need the Milky Way's mass, Andromeda's mass, and the full three-dimensional relative velocity, not just its radial component. We also need the masses and orbits of major satellites that shift the barycenter. Every parameter carries uncertainty, and uncertainties multiply when you integrate billions of years. Even the radial velocity must be handled with care because relative to what is never a trivial phrase. The often quoted approach speed depends on reference frame choices and solar motion corrections. The number is robust, but the bookkeeping matters when uncertainties are small. A few kilometers per second can matter when the tangential component is of comparable scale. The tangential velocity is where the story branches, because it sets the impact parameter of the encounter. If it is very small, the orbit is nearly head-on, and merger in about 4 to 5 billion years remains likely. If it is larger, the first encounter can be a glancing pass, with a longer delay before final coalescence. The difference is not just timing, but geometry, because tidal forces depend strongly on distance at closest approach. Some models still give a clean dramatic collision, and they do so for physically plausible parameter choices. The disks distort, the cores sink, and the system relaxes into an elliptical-like remnant after repeated passages. The timeline lands near the familiar 4 to 5 billion years, with error bars that still span human imagination. In these scenarios, dynamical friction is strong enough to erase the initial miss. Other models allow a first pass that does not immediately bind the disks together in a single catastrophic embrace. The galaxies can swing through, throw out tidal material, then separate into a long looping orbit that lasts for ages. The merger can be delayed by billions of years, even if the pair remains bound. The sky would still change, but it would change in chapters, not one climax. A few analyses even permit a near miss that looks like a flyby in the visible disks, at least on the first approach. The halos still interpenetrate and tides still act, but the closest approach can be wider. In that case, the collision becomes a prolonged gravitational relationship rather than a single event. The drama becomes slow, like continents drifting rather than mountains exploding. Bound does not mean safe, and near miss does not mean no merger, because gravity is patient. If the system is gravitationally bound, energy loss mechanisms keep working, and angular momentum can be redistributed. Over enough time, repeated passes and dynamical friction tend to end in merging. The question is whether enough time is 5 billion years or 15, but enough time is the point, because time is what distance does to plans and what uncertainty does to prophecy. A billion years is not a scheduling detail, it is a different universe of biology and climate. The Sun's evolution becomes a nearer deadline than any galactic choreography. Even Earth's long-term habitability is a more immediate variable than Andromeda's pericenter. Now we clarify the most common misunderstanding, because the word collision triggers the wrong fear and the wrong picture. Galaxies are mostly empty space, even in their disks, and the emptiness is the dominant fact. Star-star collisions are extraordinarily unlikely, because typical separations are vast compared to stellar sizes. If two galaxies interpenetrate, most stars pass by like grains of sand in a desert wind. The danger is gravitational, not impact, and gravity works on everything at once. Orbits are scrambled, gas clouds are compressed, and star formation can spike as shocks ripple through the interstellar medium. Tidal forces fling stars into long tails, and some stars are ejected into intergalactic space. The most spectacular structures are often the faintest, visible only in deep exposures. The halos meet first, long before the bright disks overlap, and that early meeting sets the tone. Dark matter passes through dark matter, yet the gravitational potential changes everywhere, reshaping both galaxies from the outside in. The visible fireworks are late, and the invisible rearrangement is early. In a simulation, you see two ghostly spheres overlap, then the luminous spirals respond like ripples on water. When the disks do interact strongly, the sky changes slowly but relentlessly, and slowness is part of the terror. Constellations shear, the background brightens, and familiar patterns dissolve as the Milky Way's disk warps. Over millions of years, the night becomes a record of orbital mechanics, with Andromeda swelling from a smudge to a dominating arc. The change is too slow for a human eye, yet unstoppable on geological timescales. Tidal tails would stretch across the sky like pale brushstrokes, and star-forming regions would glitter in knots. Dust lanes would twist, and the galactic centre might brighten as gas flows inward. Yet even then, the stars themselves remain mostly untouched by direct contact. The violence is in the collective field, not in individual collisions. Yet this is not the end of the local group story, it is the local group's definition. The Milky Way, Andromeda and their satellites are a gravitational family, bound by shared dark matter and shared history. Their future is a dance constrained by mass, motion and the unseen halo scaffolding. The word family is accurate because the members cannot simply drift apart. Now we connect this to the central question, because scale is never just awe and never just spectacle. Even if a merger is certain, it unfolds on timescales that defeat biological continuity and mock human planning. Even if a near miss occurs, it still proves that galaxies are not reachable by intention, only by gravity. Our narratives of exploration collide with the physics of distance. The local group is the largest neighbourhood where travel is even conceptually imaginable, and even here it is almost absurd. Beyond it, the distances become multi-million light-year gulfs with multi-million-year message delays. The honest measurement turns nearby galaxy into an operational impossibility. In that sense, Gaia is not just measuring motion, it is measuring limits. So Gaia's role is not to give comfort, but to restore uncertainty where headlines claimed certainty, and to show exactly why. It tells us what we can measure, what we cannot, and how small errors propagate into billion-year futures. It turns a mythic collision into a probabilistic forecast, where confidence is earned and never free. The reopened case is not a failure, but a more mature kind of knowledge. What would resolve the case is not one dramatic new image, but better constraints that accumulate like layers of varnish. Longer Gaia baselines reduce proper motion errors because the same angular drift becomes easier to separate from noise. Improved modelling of systematics tightens the reference frame, especially at the microarc-second level where biases live. Better mass estimates for the Milky Way, Andromeda, the LMC and M33 shrink the family of futures. Future surveys add leverage by mapping more traces and more of the halo, filling in the dark with motion. Stellar streams, satellite proper motions and halo star kinematics constrain the gravitational potential. Each new constraint is a nail in the uncertainty, but the coffin is not closed yet. The local group is a laboratory that takes billions of years to run, and we are reading it mid-experiment. Now we build the next rung because the ladder does not stop at our island and the view only gets colder. Whether collision or near miss, the local group remains bound, a small archipelago in a much larger sea. And beyond that sea is the deeper terror, the one that does not care about our local dances. The universe is expanding in a way that does not merely separate galaxies, but accelerates their separation over time. It accelerates, and it builds horizons that harden with time, turning distance into a one-way wall. It threatens to lock every gravitational family onto its own island, forever watching other islands fade into unreachable ghosts. The night sky itself becomes a story of loss. So the question shifts, and the tone darkens, because the scale of exile grows. If even our nearest great rival is reachable only by gravity, what does accelerating expansion do to every other destination? The next chapter follows that expansion outward, until distance becomes permanent exile. The Milky Way is not alone in the dark, and it is not truly free, even if the night sky suggests otherwise. Around us is a small community of galaxies, bound by gravity and time, moving in patterns that are slow enough to feel permanent. Call it the local group. It is not a poetic label, it is a physical claim, and it carries a measurable meaning. It says there is a region where expansion loses and gravity still wins, at least for now. Start with the map, because maps expose what words try to soften, and they reveal the hierarchy at a glance. Two giants dominate the ledger, and everything else is written in smaller print. The Milky Way and Andromeda hold most of the mass, and their dark halos do most of the holding. Andromeda, M31, is not just a bright smudge in binoculars, it is a full spiral galaxy with a vast stellar halo. Its disk is tilted toward us, and its outer regions fade into a low surface brightness glow that only long exposures can collect. When you see it in a photograph, you are seeing a system that rivals ours in scale and probably exceeds it in mass. Triangulum M33 is the third spiral, smaller but not negligible, and it complicates the family dynamics. It orbits within the same shared potential, and it can trade momentum in future encounters, like a third body in a slow gravitational negotiation. Its spiral arms are looser, its central bulge is modest, and its gas is still forming stars with a steadier rhythm. Around these three are dozens of dwarf galaxies, some bright enough for old catalogues and early telescopes. Many are so faint they were found only with modern digital surveys, where algorithms can notice what the eye would miss. Some are dwarf irregulars, still rich in gas and scattered star formation. Others are dwarf spheroidals, dim, gas-poor and dominated by dark matter, like embers held together by gravity alone. The census keeps changing because the sky is not empty, it is simply dim, and our instruments keep learning how to see. Every deeper survey turns blank space into structure, then turns structure into history, and then turns history into a new mass estimate. Even the act of counting becomes a test of cosmology, because the number of small satellites is tied to how dark matter clumps. The scale is a few million light-years across, measured from one edge to the other, depending on how you define membership. That number sounds small in cosmology, where distances are counted in billions. It is still brutal on any biological clock, and it turns patience into a required technology. If Andromeda is 2.5 million light-years away, then the local group is not a step, even in the most generous language. It is a gulf that only looks manageable on a poster, where a line can cross it in silence. In reality, light itself needs 2.5 million years to make the trip, and that is the fastest messenger the universe allows. Now we widen the frame because the disk is not the whole story. The local group is mostly dark matter, and the galaxies are bright tracers in a deeper well, like lanterns hung inside a cavern. The stars show us where matter is cooled and condensed, but the dominant mass is invisible and extended. Each major galaxy sits inside an extended halo, far larger than its visible disk, and the halo does not end where the starlight ends. The Milky Way's stellar disk is about 100,000 light-years across, yet its dark halo may extend several times farther. Those halos overlap in influence long before starlight overlaps in space, and that overlap is where local becomes a gravitational fact. This is where the chapter's core idea begins, and it is more precise than it sounds. The local group is not just nearby galaxies listed by distance and brightness. It is a gravitational basin that defines what can remain together and what must eventually drift away. To understand that basin, we need one harsh concept that astronomy borrows from mechanics. Bound versus unbound is the difference between a neighborhood and a passing crowd, and the difference is written in energy. It is not about being close today, it is about whether the future keeps you close. Bound means the total energy is negative in the shared gravitational potential, after you count both motion and gravity. Unbound means the object has enough kinetic energy to escape forever, even if it takes billions of years to do it. In plain terms, bound objects are on orbits, while unbound objects are on one-way trajectories. Escape is not a moral word, it is a speed requirement, and speed is always measured relative to mass and distance. Escape velocity is the threshold where motion beats gravity, given mass and distance, and it changes depending on where you are in the well. In a deep potential, the same object needs far more speed to leave. Near Earth, escape velocity is about 11 kilometers per second, a number that helped define the early space age. In a galaxy, the numbers rise to hundreds of kilometers per second, and the well extends for hundreds of thousands of light years. In the local group, the well is larger still because it is the combined mass of multiple halos layered together. For the local group, the escape speed depends on where you start, and on how much dark matter is truly there, which is still debated. We do not know the halo profiles perfectly, and that uncertainty is not cosmetic. It changes the depth of the prison, and it changes the meaning of leaving, because a slightly heavier halo can hold a great deal more tightly. This is a callback to Voyager and the definitional trap of boundaries, where a crossing can be real and still misleading. Voyager crossed the heliopause, yet the Sun's gravity still owns its future, and it will remain bound to the solar system for a very long time. The local group repeats that lesson at a higher rung, where the borders are not walls but gradients. You can cross a visible edge and still be trapped inside the dominant gravitational claim, because visibility is not ownership. The starlight boundary is a convenience for the eye, not a limit for gravity. In that sense, the local group is a lesson in humility. The true structure is the one we cannot see. Now we translate that into method, because method is what turns mystery into accounting. Astronomers test binding by measuring velocities and comparing them to mass models, and then checking whether the numbers can be reconciled. The work is part observation, part inference, and part careful skepticism. Radial velocities come from Doppler shifts, and they are the easy part because spectra carry their own ruler. You split a galaxy's light, find the shifted absorption lines, and read off the speed along our line of sight. Proper motions are tiny angles, and they are the hard part, especially beyond the Milky Way, because the sky changes slowly at that distance. For Andromeda, even a micro-arc second per year matters, and measuring it requires long baselines and exquisite calibration. The Hubble Space Telescope and radio interferometry have made progress, but the uncertainties remain large enough to leave room for different futures. Even with imperfect data, the broad conclusion holds, and it holds across multiple techniques. The local group is gravitationally bound, and cosmic expansion does not tear it apart today, despite the universe's overall growth. That sounds like comfort, until we ask why. Because the surrounding cosmos is not gentle. The universe is expanding, and on large scales expansion dominates, so why does our local patch resist it? Because expansion is not a force that shoves everything apart equally, like an explosion in a room. It is a metric growth of space that matters most where gravity is weak and distances are vast, and it is almost irrelevant inside dense systems. Inside a deep potential well, matter can decouple from the Hubble flow, and the local group is one of those decoupled regions. The local group is a small island that stopped expanding with the rest, long ago in cosmological terms. The island metaphor is accurate, but it hides the real mechanism, which began in the early universe. The local group formed from overdensities in the early universe, where gravity amplified small fluctuations in the primordial density field. Those fluctuations were not random sprinkles of galaxies, and they were not placed by chance. They were the seeds of a scaffold, and that scaffold is what we call the cosmic web, a pattern that simulations reproduce with unsettling fidelity. In the first few 100 million years, dark matter collapsed into filaments and knots, and ordinary gas followed because it could not ignore gravity. Now we build the next rung, because the ladder does not stop at our island. The local group is a node in a larger structure of filaments and voids, and that larger structure is the true map of the nearby universe. When we zoom out, the galaxies stop looking like isolated cities and start looking like lights strung along highways. Filaments are long threads of matter, mostly dark, connecting clusters and groups, and they can span tens to hundreds of millions of light years. Voids are the opposite, huge regions with far less matter than average, where galaxies are sparse and widely separated. Galaxies form and live along the filaments because that is where the mass collects, and where gas can cool into stars. The web is the reason the universe has texture instead of uniform fog, and it is also the reason distance is not evenly distributed. We infer the web through galaxy surveys, gravitational lensing, and simulations, each one filling a different gap in the picture. We do not see dark matter directly, yet its gravity draws the visible pattern like iron filings around a magnet, and the analogy is more than poetic. This connects to the unresolved dark matter mystery from earlier chapters, and it keeps returning because it keeps explaining things. We can map the halo's pull through rotation curves and satellite motions, and we can weigh groups through their internal velocities. We still do not know what the substance is, and that ignorance remains one of the most consequential gaps in modern physics. The ignorance matters because dark matter is the architecture of reachability, not just a bookkeeping term. It sets where groups form, how deep they are, and how long they remain coherent against the universe's expansion. The local group is therefore not an accident of geography, and it is not a casual neighbourhood. It is a product of the web, a small knot in a filamentary network with a history that began before any star existed. But the web has another implication that feels colder once you think like a traveller. Structure is not evenly spaced, so travel is not evenly priced, and the empty places are the real cost. In a uniform universe, you might imagine a steady ladder of destinations, each one a predictable step outward. In the real universe, you get clumps separated by emptier stretches, and the emptier stretches are the real barrier. The void is not merely nothing, it is distance without help, and distance without help becomes a kind of veto. Now we return to the local group's internal life, because bound systems are not static, even when they look calm. A gravitational family is not a museum, and it does not preserve its members in glass. It is a slow machine that grinds, converting orbits into heat and structure into debris. Tidal forces are the first tool of that machine, and they work with relentless subtlety. Tides are differential gravity, pulling harder on the near side than the far side, and that difference stretches objects over time. In galaxies, tides can puff up stellar disks, distort gas, and peel away the outskirts of small companions. Over time, tides stretch satellites, heat their stars, and strip their outer layers, even when nothing hits anything. A dwarf galaxy can be unmade without any direct collision, only by repeated close passages, each one shaving off a little more. The result is not a clean disappearance, but a trail. This is not theory alone, it is visible evidence around our own galaxy, if you know how to look. The Milky Way's halo is threaded with stellar streams, faint ribbons from disrupted companions, spread across the sky like smoke in slow motion. In deep surveys, these streams appear as overdensities of ancient stars, coherent in motion even when they are diffuse in light. Streams are not decoration, they are forensic traces, and they preserve orbital paths for a very long time. They reveal the gravitational potential that shaped them, because the stream's curvature and thickness encode the mass distribution it moved through. In that sense, a stream is both a remnant and a measuring instrument. Gaia made this evidence unavoidable by mapping precise stellar motions across the Milky Way, turning the halo into a kinematic dataset. It showed that the halo is not smooth, and it is not quiet. It is a graveyard of mergers still settling, with substructures that betray multiple infall events. The Sagittarius stream is a famous example, wrapping around the Milky Way like a torn seam, and it is still being pulled apart. It tells us a dwarf is being eaten right now in slow motion, and the timescale is measured in orbits rather than headlines. Other streams and overdensities repeat the message, and they do it with different ages and different geometries. The Milky Way grew by cannibalism, and it is still growing the same way, because gravity does not retire. Andromeda shows the same behaviour, with its own halo substructures and streams, some even more dramatic than ours. The pattern is universal because gravity has only a few ways to build big objects, and merging is the most efficient. Mergers are not rare accidents. They are the default growth channel, and the early universe was even more merger-rich. Small galaxies fall into bigger halos, lose energy, and become part of the host, sometimes leaving behind a thickened disk or a puffed-up bulge. The scars can persist as chemical signatures, where stars carry the elemental ratios of their birth environments. Dynamical friction is the quiet accountant behind this process, and it sounds gentle until you see what it does. A moving mass creates a gravitational wake in the surrounding halo, and the wake drags back, stealing orbital energy. Over billions of years, that drag shrinks orbits and turns companions into debris, and the bookkeeping always favours the giant. The local group is a merger engine, and the giants are its final collectors, even if the schedule is measured in billions of years. This is where the title becomes literal, and it becomes uncomfortable. The local group is a gravitational prison because escape requires extreme speed and extreme time, and both are expensive in physics. It is also our only refuge because binding creates stability, and stability is what allows complex structures to persist. A bound group can hold gas, recycle material, and keep galaxies close enough for interactions that trigger star formation. A lone galaxy in a void would be more isolated, and isolation is not neutral, because it limits fresh inflow and reduces encounters that reshape evolution. Now we connect this to the central question, because scale is never just awe, and it always becomes policy. When we measure the universe honestly, structure decides what is even reachable, and what is only visible. The local group is the largest region where intergalactic travel is not immediately absurd, even before we discuss engineering. Even here, the distances impose million-year delays for light, and far longer for ships, and those delays reshape meaning. At 1% of light speed, crossing to Andromeda takes roughly 250 million years, which is longer than many species survive on Earth. At 10%, it still takes 25 million years, and biology does not survive that unchanged. The travel problem is not only propulsion, it is continuity. because the mission becomes a different kind of entity. A mission that lasts millions of years is not a voyage, and it is not a story with a return. It is a lineage, a drifting civilization, or a machine that outlives its makers, carrying purpose across evolutionary time. Communication is trapped by the same physics, and it is trapped even more cleanly. A message to Andromeda takes 2.5 million years one way, and the silence in between is not negotiable. A reply arrives after 5 million years, if anyone is still there, and if they still speak in a recognizable way. That turns dialogue into geology, because the timescales match the reshaping of continents and climates. It turns diplomacy into archaeology, because you are always answering the dead or the transformed. It turns every plan into a bet against evolution, and against the slow drift of cultures. So the local group feels like a prison even before we mention expansion, because the bars are made of time. It is already a scale that breaks institutions, cultures, and bodies, unless those institutions are redesigned around deep time. Yet the deeper limit is not inside the group, and that is the next reveal. The deeper limit begins at the group's edge, where the Hubble flow reasserts itself, and where the universe resumes its general behaviour. Now we measure the boundary, because boundaries are what define our true size, and they define what local really means. The local group has a notional edge where gravity no longer binds galaxies to the group, and where the average expansion wins the tug of war. Outside that edge, galaxies participate in the general expansion of the universe, and their recession is not because they are flying through space. It is because space between us grows, and the growth accumulates like interest. This is where a common intuition fails, because the mind reaches for familiar chases. You can imagine chasing a receding galaxy like chasing a car, where speed is all that matters. Expansion is not a car, it is the road stretching, and the stretching can continue while you accelerate. In the bound region, the road does not stretch enough to matter, because gravity keeps the local metric from drifting away. Beyond it, the stretching dominates, and the cost of travel changes character, from difficult to structurally unstable. Distance in an expanding universe is not just meters to cross, it is a moving target with a clock attached. The clock does not stop for your engines, and it does not pause for your intentions. The farther you aim, the more the universe changes while you travel, and the destination is not waiting in place. The separation can grow while you burn fuel, and that possibility changes what arrival even means. This is the existential price increase, and it is not linear like paying more for more miles. It is structural, because expansion can outrun any finite strategy over enough time, and because the background itself is evolving. Even if you could travel near light speed, you still face horizons, and horizons are not metaphors here. There are regions whose light reaches us today, yet no signal we send today can ever reach them, no matter how long we wait. That is not science fiction. It is the consequence of accelerating expansion, and it is supported by the same equations that predict the cosmic microwave background. It is the universe turning visibility into a one-way privilege. But before we go there, we lock in the local group's role, because it is the last place where the old intuition still mostly works. It is a rare pocket where gravity still defeats expansion, and that pocket is shrinking in relative importance as the universe grows. As the universe ages, dark energy drives faster expansion on large scales, and the far structures recede more quickly. More distant groups recede faster, and the web's connections thin into isolation, as if the filaments are being stretched into invisibility. In the far future, each bound group becomes its own island universe, not by building walls but by losing contact. The local group will remain, while other groups fade beyond any reachable boundary, and eventually beyond any detectable one. This is why the local group is both prison and refuge, and why the phrase carries a double weight. It limits our physical options, yet it may be the only large reservoir we can ever influence, harvest, or meaningfully explore. The same gravity that traps us also keeps resources from running away. Now we return to the cosmic web, because the web explains why this isolation is not evenly distributed, and why our view is deceptive. Filaments feed groups and voids starve them, and the pattern determines who has neighbours. Our local group sits near larger structures, including the Virgo cluster at tens of millions of light years, and we feel its influence in our motion. Virgo is massive, and it anchors a larger assembly of galaxies, but it is already far beyond any plausible biological travel. We can see Virgo, measure it, and model its pull on our motion, including the subtle dipole pattern in the cosmic microwave background that reveals our velocity. Seeing is not touching, and the gap between those verbs is widening with time. This is the same divergence promised in Chapter 5, and it is the documentary's persistent sting. The observable universe is not the reachable universe, and the difference grows as expansion accelerates and horizons harden. The local group is therefore the last rung where the word neighbour still has operational meaning. Beyond it, neighbour becomes a visual category, not a navigational one, like a mountain seen across an uncrossable sea. Now we convert that into time, because time is what distance does to plans, and it is what turns maps into fate. A civilization can adapt to long projects, but only if the environment stays coherent enough for the project to remain the same project. Over millions of years, stars evolve, orbits shift and galaxies merge, and the sky itself changes its geometry. Over billions, the cosmic web becomes less connected, and opportunities close, not because of malice, but because of mathematics. The local group gives us a limited window where nearby galaxies remain in gravitational conversation, exchanging matter and momentum. That conversation is violent in slow motion, and it ends in mergers, because bound systems relax toward fewer, larger bodies. Milky Way satellites will continue to fall in, shedding streams and globular clusters, and enriching the halo with stars of different origins. Andromeda's satellites will do the same, feeding its halo and thickening its outskirts, and leaving their own faint signatures. M33's fate is uncertain in detail, but not in tone, because three-body dynamics rarely preserve the smallest member. It will be torqued, stripped, or absorbed as the giants exchange energy and angular momentum, and its gas may be stirred into bursts of star formation. The local group's future is consolidation, and consolidation is a kind of erasure. Gravity turns diversity into a single remnant, and the web's larger-scale expansion ensures there is no replacement supply, no new infell from far away. This is the bleak symmetry of cosmology, and it is almost elegant. Locally, gravity pulls everything together, while globally, expansion pushes everything apart. We live in the overlap where both truths apply, and where the boundary between them defines our real size both physically and philosophically. Now we connect this back to the earlier cartography limits, because even our map of the local group is incomplete, and incompleteness is a scientific condition. Dust hides faint stars, and distance hides faint dwarfs, and low surface brightness objects can vanish into the background. We still debate the Milky Way's far side structure, the exact spiral pattern, and the halo's shape, because we live inside the disk we're trying to chart. Those uncertainties propagate upward when we model group binding and future mergers, and they widen the range of predicted outcomes. We also still debate the total masses of the Milky Way and Andromeda, and different methods disagree by factors that matter. Some methods use satellite velocities, others use stellar halo kinematics, and others use timing arguments that treat the Milky Way and Andromeda as a two-body system. The disagreements change escape speeds and encounter timelines, and they change how tight the prison feels. Yet the chapter's claim does not depend on perfect numbers, and it does not need a single definitive mass. Whether the local group is 3 million light-years wide or 5, it remains a tiny island in a vast sea, and the sea is expanding. And whether Andromeda merges in 5 billion years or 15, the local group remains bound because the long-term energy budget is still negative. The prison bars are not made of steel, they are made of space-time geometry, and geometry does not bend to desire. Now we build the next rung because the ladder does not stop at our island, and the next rung is where the optimism breaks. Outside the local group, the Hubble flow dominates, and the universe becomes a moving map where distance is dynamic. This is the key limit we introduce here, and it is a limit of structure. Reachable space may be capped not by engines, but by cosmic structure and cosmic time, and those are indifferent constraints. A ship can fight inertia with fuel, but it cannot negotiate with an accelerating boundary, and it cannot demand that distant galaxies remain within causal reach. The universe does not promise that destinations stay destinations, so the local group becomes our only realistic arena for physical expansion, at least in any sense that resembles exploration. It is the largest region where gravity keeps targets from fleeing faster than we can chase, and where the map does not dissolve while you travel. That is the terrifying truth hidden inside the phrase local group. Local means bound, and bound means the future is shared, whether we like it or not. Local means possible in principle, while everything else becomes a fading photograph, a record of places that cannot be touched. Now we end on the transition that changes the documentary's stakes, because the next step is not another map. To understand why intergalactic travel may be permanently impossible, we must confront expansion, and we must treat it as an active boundary. Not as a background fact, but as an accelerating wall that erases destinations, even while it lets their light arrive. The next chapter follows that boundary outward, until the universe itself becomes the wall. You have been told the universe is big, but not what bigness does to hope, planning, or the meaning of someday. This chapter is where distance stops being a number and becomes a disappearing target, one that slides away while you measure it. We leave the local group's gravity well and step into the Hubble flow, where expansion becomes the default background condition. Out there, the map itself evolves while you travel, and it does not wait for your engines to warm. Start with the plain rule that rewired astronomy in the 20th century, because it turned the sky into a timeline. In the 1910s and 1920s, Vesto Slipher measured galaxy spectra, and Edwin Hubble tied those redshifts to reliable distances. Hubble's law says the farther a galaxy is, the faster it recedes from us, and the trend is remarkably clean at large scales. The relationship is simple in form, speed is proportional to distance, yet its consequences are anything but simple. At twice the distance, the recession rate is roughly twice as large, so the farthest objects are carried away the fastest. In modern terms, the proportionality constant is the Hubble constant, which sets today's expansion rate in kilometers per second per megaparsec. That number is not merely a statistic, because it becomes a clock for cosmic history and a constraint on cosmic fate. This is not a claim about galaxies firing outward from a central explosion, as if the Milky Way sits at the center. It is a claim about space itself, expanding between all widely separated points, so every observer sees the same general pattern. If you lived in another galaxy, you would watch us recede too. Cosmic expansion has no privileged address. The better mental image is not shrapnel, but a stretching fabric where separations grow even when objects hold still. On screen, imagine a faint grid drawn across darkness, its lines slowly widening while clusters of points keep their own shape. Now, we clarify the trap, because language makes expansion sound like ordinary motion, and ordinary motion has the wrong rules. A galaxy can be nearly at rest locally, yet still recede cosmologically, because recede here means the metric grows. The recession is not measured as a rocket speed through space, the way radar measures a spacecraft leaving Earth. It is measured as the stretching of the metric that defines distance itself, which is why the bookkeeping feels unfamiliar. In general relativity, the universe is described by a scale factor that changes with time, and that change multiplies large separations. Light travelling through that stretching space gets its wavelength stretched too, which is why the spectrum slides toward red. Redshift is therefore a record of expansion, not only a Doppler effect, even though Doppler language is tempting. A Doppler shift comes from motion through space, but cosmological redshift comes from space changing under the light's feet. In the local group, we saw a crucial exception that proves the rule, because gravity can carve out islands in the flow. Andromeda is blue shifted because gravity dominates at small enough scales, pulling our galaxies toward a future collision. That is the same lesson as Voyager's boundary problem, scaled upward from plasma to galaxies and from years to eons. Crossing a named edge can be real, yet the deeper ownership remains gravity, which keeps writing the rules underneath. The heliopause was not the end of the Sun's domain, and it never was, because the Oort cloud, if it exists, extends far beyond. The Hubble flow is not the end of gravity's domain, and it never is, because bound systems simply refuse to expand. Bound structures resist expansion because their internal forces set their own scale, and that scale becomes self-enforcing. Atoms do not expand because electromagnetism holds their sizes fixed, locking electrons into quantized states around nuclei. Planets do not drift from stars because gravity binds their orbits tightly, and orbital energy is not diluted by the Hubble flow. Galaxies do not expand with the universe because their self-gravity decouples them, keeping stars on stable trajectories. Even galaxy clusters can remain intact when their total binding beats the Hubble pull, though their outskirts can be delicate. Expansion dominates only where matter is thin and gravity cannot lock distances, which is most of the volume between structures. If the universe were a city at night, The bright neighbourhoods would stay compact, while the dark countryside slowly stretches. Now we widen the frame, because the key is what counts as bound, and the answer depends on density and time. Between galaxy groups, the average density is low and the web is stretched, with filaments and voids sculpted by gravity. Across tens of millions of light years, gravity is too weak to freeze the metric, so separations participate in expansion. Those separations ride the Hubble flow, and the recession becomes the baseline against which all motion is measured. The local group is an island because it stopped expanding with its surroundings long ago, when its matter fell together. Outside that island, the ocean is not water, it is growing space, quiet, cold, and indifferent to your intentions. Visually, the camera pulls back until the local group becomes a glowing knot, surrounded by widening black lanes of void. Hubble's law gives a recession rate that rises with distance until it becomes unsettling, because the line keeps climbing. At some distance, the recession rate exceeds the speed of light, and the graph crosses a boundary that feels forbidden. That sounds like a violation, until we remember what is and is not forbidden, and where relativity draws its red lines. Nothing locally moves through space faster than light in its own neighbourhood, because local measurements obey special relativity. Relativity forbids superluminal motion through space, not superluminal expansion of space, which is a different statement. The speed limit is local, while expansion is global bookkeeping of geometry, and geometry is not a rocket you can chase. A photon still outruns everything nearby, yet distant galaxies can recede faster than that photon can reduce the gap. This is where the documentary's central question sharpens into a harder form, because far becomes forever. When we measure the universe honestly, reachability is not the same as visibility, even though our instincts merge them. A galaxy can be visible today because its old light is already en route, crossing space that used to be less stretched. Yet it can be unreachable today because new signals can never catch up, no matter how perfectly you aim them. The universe can show you places it will not let you touch, like a museum behind glass that only time can thicken. That is not poetry, it is causal structure, and it is encoded in the way the scale factor evolves. Now we translate that into method, because method is what turns mystery into accounting, and accounting is what convinces skeptics. Astronomers did not infer acceleration from one instrument or one data set, because a single tool can always mislead. They built a case from independent pillars that converge on the same conclusion, even when their systematics differ. The first pillar came from Type Ia supernovae used as standardizable candles, discovered in surveys that watched the sky repeatedly. Type Ia explosions occur when a white dwarf is pushed toward instability, producing a characteristic brightness after calibration. Their intrinsic brightness can be inferred from their light curve behavior, because brighter events fade more slowly in a predictable way. Compare inferred brightness to observed brightness, and you get distance, after correcting for dust and instrumental bias. Compare distance to redshift, and you get the expansion history, because redshift tells you how much the universe stretched. The supernovae were dimmer than expected in a decelerating universe, even after careful corrections and cross-checks. Dimmer meant farther, and farther meant the universe expanded more than predicted, leaving extra stretch along the light's path. The simplest reading was that expansion has been speeding up over time, so the scale factor's growth began to accelerate. Acceleration was not a philosophical preference, it was a fit to the data, and the residuals pointed the same way. The result was shocking because gravity should slow expansion, not amplify it, at least if matter and radiation are the whole story. Historically, this was a reversal of expectation, because many cosmologists had spent decades debating only how fast deceleration occurred. The second pillar is the cosmic microwave background, the afterglow of the early universe, released when atoms first formed. When the universe cooled enough for electrons and protons to combine, photons stopped scattering constantly and began free streaming. That last scattering light reaches us as microwaves, nearly uniform, with tiny temperature variations at the level of parts per 100,000. Its temperature pattern encodes geometry, composition, and the growth of structure, like an imprint left in cooling wax. The CMB tells us the universe is close to spatially flat on large scales, meaning Euclidean geometry is a strong approximation. Flatness ties the total energy density to a critical value, a balance point between open and closed spatial curvature. Matter alone falls short of that critical density in multiple measurements, including galaxy clustering and gravitational lensing. Something else fills the budget, and it behaves unlike normal matter because it does not clump the same way. The third pillar is large-scale structure, the cosmic web's pattern and evolution, mapped by surveys counting millions of galaxies. Galaxies cluster in a way that depends on how fast structures grow, because gravity tries to amplify small, early fluctuations. Acceleration suppresses growth because expansion pulls matter apart faster, reducing the time gravity has to gather it. Surveys of clustering and baryon acoustic oscillations trace that history, using a standard ruler left by early universe sound waves. The pattern matches a universe dominated late by a smooth, persistent component, one that becomes important as matter thins out. These pillars agree within uncertainties, and that agreement is the real weight, because it is hard for three methods to share one illusion. We call that component dark energy because it is inferred, dominant and unknown, and the name is an admission of ignorance. The simplest model treats it like a cosmological constant, constant in time and space, the same everywhere and everywhen. Historically, Einstein introduced a constant to hold the universe static, then abandoned it after expansion was discovered. Now the constant returns, not as a preference, but as a minimal term that matches the acceleration seen in the data. In equations, it looks like an energy density of the vacuum itself, an intrinsic property of empty space rather than of matter. Its pressure is negative, which makes it gravitationally repulsive in the expansion equation, even though that sounds paradoxical. In plain language, negative pressure means the energy does not dilute as space grows, so its influence becomes dominant over time. That negative pressure drives acceleration without needing a new force in local space, because it changes the universe's overall dynamics. We do not claim to know what it is, only what it does to the scale factor, and that distinction matters in science. Now we connect this to earlier mysteries because ignorance has a pattern, and the universe keeps exploiting our blind spots. Dark matter was inferred from gravity we could not see, and it built galaxies, holding them together with invisible mass. Dark energy is inferred from expansion we cannot stop, and it unbuilds connections, thinning the network of reachable places. Both are measured by their effects, not by direct detection in a laboratory, which makes them powerful and frustrating. Both turn our cosmic map into an inference problem with high-stakes consequences, because the map controls what is possible. Acceleration changes the meaning of distance because it creates horizons, and horizons are where possibility ends without a barrier. A horizon is not a wall in space, it is a boundary in space-time, defined by how light cones tilt as the universe evolves. It is defined by what signals can reach you, not by what you can imagine, and imagination does not bend geodesics. In cosmology, there are two horizons that people confuse, and the difference matters, especially when you talk about the edge. The particle horizon is about what we can see today, a limit set by how far light has travelled since the beginning. It marks the farthest distance from which light has had time to reach us since the beginning, given the expansion history. Because the universe expanded while that light travelled, the particle horizon is far larger than age times c suggests. The observable universe is defined by this horizon, and it is already enormous, filled with galaxies whose light is ancient. But observable does not mean reachable, and it never promised to, because seeing is a passive act and travel is an intervention. A visual diagram helps here. A widening cone of past light meets the present, and everything inside that cone is visible. The event horizon is about what we will ever be able to see or influence in the future, even if we wait forever. It marks regions whose light emitted now will never reach us, even given infinite time, because expansion outruns the photons. In an accelerating universe, this horizon is finite, and it hardens with time, like a closing gate made of geometry. It is the ultimate communication limit because it is built into the equations, not into technology or politics. A signal sent today can be trapped behind it, not by absorption but by expansion, as the intervening space grows too quickly. If the particle horizon is a record of what has already arrived, the event horizon is a rule about what never can. Now we measure the boundary, because boundaries define our true size, and true size here means causal reach. There are galaxies whose ancient light reaches Earth tonight, landing on detectors as faint smudges and stretched spectra. Yet any message we transmit tonight will never arrive at those galaxies, even if the message rides a perfect laser beam. The light we see is a fossil record from when they were closer in space-time, when their world lines lay within future contact. The universe lets the past arrive, while it denies the future a path, and that asymmetry is the point. That asymmetry is the terrifying part because it turns knowledge into a one-way gift, delivered without the possibility of reply. This is not a contradiction, it is a consequence of changing expansion rate, and it can be drawn cleanly on a space-time diagram. Light that started long ago can cross regions that were once inside causal reach, because earlier expansion was slower. As acceleration strengthens, the remaining distance grows too fast for new light to overcome, so the same route closes behind it. The boundary is therefore time-dependent, and it moves as the universe evolves, shrinking the set of futures we can touch. The horizon is not where galaxies are now, but where their world lines go, and world lines are the real addresses in relativity. On screen, imagine world lines as threads, some bending outward until they slip beyond the region our future light cone can cover. Now we convert that into travel, because time is what distance does to plans, and plans are what civilizations are made of. Imagine a ship that can cruise at near light speed for as long as it wants, with fuel, shielding, and patience solved. In a static universe, near light speed would eventually reach any destination, because the distance would not change underneath you. In an expanding universe, your path is not a fixed corridor, because the corridor lengthens while you cross it. In an accelerating universe, some destinations recede faster than your progress, so your remaining distance can stop decreasing. You can pour energy into speed, yet the space you must cross keeps increasing, and the chase becomes a mathematical loss. The chase can be lost even when you never slow down, because the target is not running, it is being carried by the metric. This is the core twist that most scale diagrams hide, because they draw space as if it were a frozen stage. The universe is not just large, it is actively removing options, and it does so more efficiently the farther you aim. The farther you aim, the more the target's recession rate matters, because recession grows with distance in the Hubble flow. At sufficient distance, the required average speed exceeds what physics allows locally, even if your engines are ideal. Even if you approach light speed, you cannot outrun a horizon defined by space-time, because horizons are not obstacles you can dodge. The reachable universe is therefore smaller than the observable universe, and that difference is the price of acceleration. Now we clarify what does not happen, because the wrong picture spreads easily, and it makes the universe seem haunted. The Milky Way does not expand internally as dark energy pushes on its stars, because internal gravity dominates by many orders of magnitude. The solar system does not loosen because the scale factor increases elsewhere, since orbital dynamics are set by local curvature. The Earth does not drift from the Sun because the metric expands between galaxy clusters, and no hidden, stretching wind blows here. Local binding cancels expansion by setting stable orbits and stable sizes, so rulers and atoms do not quietly inflate. Expansion is a large-scale behavior of the average universe, not a universal stretching of everything, and that distinction is essential. This connects back to the definitional trap we set with Voyager, because boundaries are always about which physics dominates. We learned that interstellar depends on which boundary you mean, and the same word can hide multiple realities. The heliopause is a plasma boundary, while the Oort cloud is a gravitational hypothesis, inferred from comet statistics and dynamics. Even if the Oort cloud exists, it is a fuzzy inferred reservoir with uncertain edges, and its membership is probabilistic. The honest definition was never about a headline crossing, but about what still holds you and what can still pull you back. Cosmic expansion repeats the lesson. What matters is the binding, not the label. Because binding decides what resists the flow. Now we build the next rung because the ladder does not stop at our island, and the next rung is emptier than intuition expects. Beyond the local group, most galaxies are not neighbours in any operational sense, even if they look close in a telescope. They are part of the Hubble flow, and their separation grows as a baseline condition, like interest accumulating on a debt. A traveller does not just cross distance, it crosses a distance that is changing, and the change can dominate the crossing. A communicator does not just send a signal, it sends into a geometry that may forbid arrival, regardless of signal strength. The phrase, too far, becomes too late, because the universe's future can close routes that the past kept open. The event horizon is the ultimate version of that veto, and it is indifferent to ambition, courage, or ingenuity. It says there is a sphere of influence beyond which we cannot affect anything ever, because our future light cannot reach it. It also says there are regions that will never affect us again after a certain time, because their future light cannot reach us. Causality becomes a shrinking resource, not because light slows, but because space accelerates, and acceleration tilts the accounting. The universe becomes a set of islands that cannot exchange messages, separated not by walls but by the growth of emptiness. If exploration is contact, then the event horizon is a definition of solitude, written into the expansion itself. Now we run the future sky thought experiment, because it makes the prediction physical, and it turns equations into a scene. Imagine waiting not years or millennia, but trillions of years, long enough for stellar populations to age into darkness. Stars burn out, galaxies age, and the expansion keeps accelerating, so the cosmic web thins into disconnected archipelagos. Distant galaxies continue to redshift, their photons stretch to longer and longer wavelengths, sliding from visible into infrared. Their light dims, not only by distance, but by the energy loss of redshift, because each photon arrives with less punch. Even if you build larger telescopes, the photons become rarer and colder, and the sky's information rate collapses. Visually, the familiar deep-field tapestry drains of colour, then of structure, until only a few nearby glows remain. Over enough time, the sky empties in a specific, testable way, and the emptiness has a signature rather than a mystery. Galaxies outside the local group fade, then vanish from view, one by one, as their light is stretched beyond detectability. Not because they cease to exist, but because their light can no longer reach us effectively, and what arrives becomes too diluted. The cosmic microwave background itself redshifts to wavelengths larger than any reasonable instrument, merging with the cold noise of the future. The early universe becomes observationally inaccessible, even in principle for future astronomers, because the evidence slips past their horizon. Cosmology becomes harder, then impossible, for civilizations born too late, who may see only one galaxy and a dark sky. What would they infer about the origin of everything if the strongest clues have been stretched away into silence? What remains visible is what remains bound, because binding is the universe's way of preserving structure against expansion. The local group merges into a single large remnant over long timescales, as the Milky Way and Andromeda collide and settle. That remnant becomes the only major galaxy in our sky, surrounded by dwarf companions that orbit like embers around a coal. The rest of the universe becomes a black ocean with no lighthouses, and the horizon becomes a permanent fog line. Cosmic loneliness is therefore not mood, it is a physical prediction of acceleration, and the prediction has teeth. The night sky's future is not just darker but simpler, and simplicity can be a kind of ignorance. Now we connect this back to the central question, because scale is never just awe, and awe is never just entertainment. We have treated distance as a bill, and expansion as interest that compounds, and the compounding rate is not under negotiation. Dark energy turns the bill into a deadline, because the reachable set shrinks with time, and shrinking sets hard priorities. Intergalactic travel was already biologically absurd at local group scales, because lifetimes and supplies do not scale with ambition. Acceleration makes it structurally impossible beyond a boundary, even for perfect engines, because geometry vetoes the itinerary. The universe does not just dwarf us, it isolates us by geometry, so the drama is not size alone, but separation. This is where the stakes rise beyond engineering and into causality, because causality decides which dreams are meaningful. A civilization can imagine generation ships, suspended animation, or machine descendants, and those ideas can defeat time. None of those ideas defeat an event horizon that forbids arrival, because the prohibition is not fatigue but space-time structure. You can survive the time, yet still be denied the destination, and denial is absolute when it is geometric. The universe can make exploration not merely difficult but undefined, because to go there stops having an operational meaning. So what is a frontier, when the frontier is not a place, but a closing set of future light cones? Now we end on the transition that changes the documentary's stakes, because the next limits are not cosmic but biological. Even before cosmic horizons defeat us, biology and engineering face brutal constraints, and those constraints arrive much sooner. Now we ask the forbidden question: could any living civilization ever cross these distances, even in principle, before the map closes? The next chapter stops talking about where we could go and starts counting what we can endure in time, mass, and fragility. You've been told the universe is big, but not what bigness does to living systems. Chapter 8 made distance dynamic, with horizons that erase destinations while light still arrives. Now we ask a harsher question, because biology does not get to be abstract. If physics allows a trajectory, can a civilization survive what the trajectory demands? Start with the bill we kept postponing, because propulsion is not a vibe. Kinetic energy scales with velocity squared, and that curve punishes optimism. Double the cruise speed and you quadruple the energy you must buy, store, and later throw away as heat. Push toward relativistic speeds, and the numbers stop being engineering and become civilization. A ship that is massive enough to shield life becomes expensive enough to reshape economies and priorities. A ship that is light enough to accelerate becomes fragile enough to die, because thin margins invite single-point failures. Now we translate that into method, because method is what turns mystery into accounting. Write the simplest line first, because it already hurts. Energy is 1/2 mv squared, before relativity adds its own surcharge and changes what mass effectively means. At 10% of light speed, v is 30,000 kilometers per second, a number that sounds clean until you picture it. That speed is not a sprint. It is a permanent collision with everything you meet: gas, dust, and stray atoms. At half-light speed, relativity raises the cost again, and the curve steepens as momentum becomes stubborn. At 90%, the gamma factor turns fuel into a near-infinite appetite, because each extra percent buys less speed. Even before you touch relativity, rockets face a second penalty that hides in plain sight. The rocket equation demands reaction mass, so the fuel you carry becomes the mass you must accelerate. That feedback loop is why chemical rockets top out early, and why even fusion concepts look austere on paper. When you imagine a habitat, a farm, and shielding, you're also imagining a mountain you must push. The universe does not care whether your payload is steel or childhood memories. Momentum charges the same price. The trap is not only acceleration, because arrival is a second launch. You must brake at the destination, and braking costs the same order of energy as getting up to speed. If you do not brake, you do not arrive, you just pass through as a bullet and call it a flyby. If you use the destination's environment to brake, you turn that environment into shrapnel and plasma. A near-relativistic craft carries impact energy comparable to large nuclear arsenals per ton, and the comparison is conservative. That energy must go somewhere, and physics does not care where you prefer, only where the equations allow. Now we clarify the trap, because language makes travel sound like a road trip. In space, there is no friction to help you slow down gently, and no atmosphere to bleed speed without consequences. Every meter per second you remove must be paid for with reaction mass or fields, and both require infrastructure. A civilization can spend that budget, but the spending has consequences at home, because energy is political. If you divert a planet's energy economy into a ship, you change the planet's politics and its definition of progress. If you do it for centuries, you change what the civilization even is, because the ship becomes the central institution. Now we widen the frame, because the vacuum is not empty enough. Between stars and between galaxies, there is still gas, dust, and stray atoms, spread thin but never absent. At low speeds, the interstellar medium is a nuisance and a measurement tool, because it reveals itself in absorption lines. At high speeds, sparse becomes lethal, because kinetic energy rides with v squared, and then rides again with gamma. A single hydrogen atom at relativistic speed hits like a high-energy particle beam, because in the ship's frame it is accelerated. A thin mist becomes constant radiation, delivered from the front like a headwind of bullets that never sleeps. Intergalactic space is thinner, but the distances are so long that exposure integrates into certainty. Over millions of years, even rare impacts become guaranteed impacts, because probability has time to collect its debt. Dust grains are the real nightmare, because they carry mass you cannot ignore, and mass is what makes craters. A grain the size of sand at relativistic speed releases energy like an explosive, and the shock front becomes a weapon. A grain the size of paint fleck can punch through layers and start cascades, because fragments become their own projectiles. The ship becomes a detector for everything you hoped was not there, and the readout is damage. Now we measure the boundary, because boundaries define our true size in practice. The The boundary is not the edge of the local group, it is the survivable flux across a forward-facing area. At a tenth of light speed, the forward-facing shielding must absorb relentless impacts that look like continuous micrometeorites. At half-light speed, a sparse medium becomes a continuous particle accelerator, and the bow becomes a radiation source. At near light speed, the front of the ship is a perpetual explosion surface, where each hit arrives pre-energized. You can add shielding, but shielding adds mass, and mass raises the energy bill, which then demands still more fuel. Now we connect this to the central question, because scale is never just awe. The universe is not only far, it is hostile in ways that scale with ambition and punish speed. To go faster, you must carry more protection, and to carry more, you must go slower, or spend more to compensate. The design space narrows until it becomes a single point that may not exist, a compromise between death modes. This is where physics stays polite, but biology starts breaking because biology cannot be almost safe. Radiation is the second invoice, and it arrives even if you never hit dust. Galactic cosmic rays are high-energy nuclei accelerated by supernova remnants and shocks, including iron nuclei moving near light speed. Solar energetic particles are bursts that can spike doses in hours and days, turning a calm cruise into an emergency. Inside Earth's magnetosphere, we forget how much shielding we are borrowing, because the planet is an invisible umbrella. Outside it, exposure becomes a chronic assault on DNA, tissues, and electronics, and the assault is statistically relentless. Over long durations, small dose rates become large cumulative damage, because cells keep dividing and errors keep landing. Radiation is not only about cancer, although cancer is the headline we recognize. High-energy particles break DNA directly, and they also create reactive chemistry that damages cells indirectly. In the brain, chronic exposure can affect cognition, mood, and decision-making, which matters on a ship that cannot afford drift. In electronics, single-event upsets flip bits, latch circuits, and slowly degrade materials, so even computers age like organisms. When you stretch a mission from years into millennia, reliability becomes a biological trait, selected by failure. Shielding sounds simple until you count the kilograms and then count them again. Water, polyethylene, and regolith can reduce dose, but only with thickness, and thickness is mass you must accelerate. Thickness across a habitat means tons per square meter, multiplied by surface area, multiplied by the need for redundancy. If you shield with metal, you create secondary particle showers when cosmic rays strike, because nuclei fragment on impact. The shield becomes a source, because spallation turns one particle into many, and protection becomes a generator. Active shielding with magnetic fields is speculative and power-hungry at required scales, because field strength must be enormous. Even if it works, it must work for millennia without maintenance failure, and maintenance is a social problem. Now we build the next rung because the ladder does not stop at the hull. A living ship is not only a container, it is an ecosystem with feedback loops, delays, and hidden couplings. Ecosystems drift because species evolve, microbes mutate, and balances shift, especially in closed environments. Closed-loop life support must be perfect, not for a mission, but for geological time, which is a different category. A small error in nutrient cycling becomes a slow catastrophe that no resupply can fix, because there is no outside buffer. A pathogen that adapts to the habitat becomes a permanent resident, and the habitat cannot quarantine itself. A crop blight that appears once can appear again, because the ship is the whole world and the spores never leave. Human history offers small, sharp previews of this fragility, even on a planet with oceans of redundancy. Sailing ships carried rats, scurvy, and epidemics, and those voyages lasted months, not millennia. Antarctic stations show how isolation amplifies conflict, and those stations still receive supply planes and evacuation options. Biosphere 2 showed how hard it is to balance oxygen, carbon dioxide, and agriculture, even with constant monitoring. If a sealed habitat struggles for 2 years under Earth's sunlight, what does stable mean over 1 million? Now we convert that into time, because time is what distance does to plans. Even at 1/10 of light speed, Andromeda is about 25 million years away, and that number is stubborn. That is in the Milky Way frame, and it is the frame that matters for history, because history is written at home. 25 million years is longer than the age of many genera on Earth, and it dwarfs recorded civilization. It is longer than the time since the first apes diverged from other primates, and longer than our tool traditions. It is longer than the span between mass extinctions and new dominant lineages, which is nature's reset rhythm. A biological crew does not remain the same species across that interval, because selection never stops. So the mission becomes a generational ship, and generational ships become civilizations. A civilization in Archaean must reproduce, educate, govern, and resolve conflict indefinitely, while also repairing pumps and seals. It must do this without fresh land, without new resources, and without escape, because the walls are the definition. It must do it while the outside universe offers no correction and no rescue, only indifferent starlight. The ship's culture becomes the propulsion system because morale is what keeps maintenance happening when nobody is watching. If culture fails, the ship fails, and physics never needs to intervene because neglect is enough. Genetic drift is not a footnote, because small populations evolve fast and lose diversity by chance. Even with careful planning, mutations accumulate and selection pressures change, because the environment is artificial and constant. A habitat with artificial gravity, recycled air, and limited sunlight is a new environment, and new environments sculpt bodies. Traits that help survival inside may harm survival outside, if outside ever arrives, and if outside is still habitable. Inbreeding avoidance requires large populations, but large populations require more mass and energy, and more complex governance. Cryobanks and embryo libraries can help, but they require stable power and stable institutions across deep time. Institutions are fragile when they must last longer than empires and languages, and fragility compounds quietly. Now we translate that into method, because method is what turns dread into numbers. Ask how long human institutions last, then compare it to millions of years, and notice the mismatch. States last centuries, religions last millennia, and both fracture under stress, even with shared skies and trade. A ship cannot afford civil war because there is nowhere to retreat and no hinterland to absorb damage. A ship cannot afford ideological collapse because maintenance is not optional and expertise cannot be replaced by faith. A ship cannot afford boredom because boredom becomes sabotage over generations, and sabotage becomes a system failure. The mission's purpose must be transmitted like a gene with high fidelity across births that never consented. High fidelity over millions of years is not a known property of any culture, and that is a data point. Now we clarify the trap because the dream hides behind a single word. We say travel, but what we mean is continuity across deep time, across drift, and across forgetting. The ship must preserve knowledge, tools, and meaning while everything drifts, including what counts as true. Languages change, myths replace manuals, and technical skills become ritual, because stories survive better than schematics. Even if archives survive, the ability to interpret them can vanish, because literacy is a practice, not a file. A society can lose the capability to repair its own life support, one generation at a time. At that point, the ship becomes a tomb, moving through intergalactic dark, still fast, still silent, still doomed. Information delay makes the isolation absolute, and it is the cleanest limit because it cannot be engineered away. A message to Andromeda takes 2.5 million years one way at light speed, which turns conversation into stratigraphy. Mission control becomes a fossil because every update arrives after continents reshape and species migrate. There is no resupply, because resupply is another ship with the same impossible bill, launched from a changed civilization. There is no rescue, because rescue implies faster travel than the original mission, and that implies an even worse bill. There is no real conversation, because replies arrive after 5 million years, and 5 million years is a different world. Autonomy becomes total, and total autonomy means every error is final, because there is no outside patch. Now we connect this to Voyager's definitional trap, because boundaries always mislead. Voyager crossed a plasma boundary, yet remained under the Sun's gravitational claim, still falling within a larger structure. Intergalactic travel repeats the lesson, because crossing distance is not leaving constraint, it is trading constraints. You can leave a star and still be trapped by time, radiation, and sociology, which are harder to escape than gravity. The meaningful boundary is not a line in space, it is a threshold of survivability, measured in failures per year. If you cannot keep a society coherent, you have not truly travelled, you have only launched debris with a story. Now we widen the frame, because proposed solutions arrive right on cue. Hibernation promises to turn time into sleep, reducing food, conflict and boredom, which are real costs. But hibernation must be safe for decades, then centuries, then millennia, then millions, without cumulative damage. Biology does not offer that mode, and engineering it means rewriting what a human is, down to metabolism and repair. Even if bodies sleep, systems must stay awake, and awake systems still fail, because entropy does not hibernate. A sleeping crew is not a solution to shielding, impacts or maintenance, and it does not stop cosmic rays. It is a solution to psychology, and psychology is only one failure channel among many. Mind uploading promises to remove flesh from the equation, turning crew into software that can be copied. But software still needs hardware, power, radiation tolerance, and error correction, and hardware is still matter in space. Over millions of years, bit flips accumulate, and cosmic rays do not respect your backups, especially if the backups share location. A digital mind must be copied, verified, and repaired with a rigor beyond